louder.
Okay, fine. Yeah, so today's session we are going to take on peer deck. So I want all of you to go to this joinpd.com. Just Google this joinpd.com and use this code to join this session. Okay. So all of you can go to joinpd.com. Just Google this joinpd.com and use this code SJJLOF. Do not give any space in them. So all of you can join this so that you can participate with it. So we'll start our class in another 2 minutes. So I want some more of you to join this. So how is week 10 content? It's easy compared to the previous weeks.
Yes, sir.
Yeah. Yeah, I can understand this is slightly easier. It's just that you have to understand certain concepts and just keep applying it. And even the questions won't be any tricky or, like we can't do much about it. Just that we have to give some direct questions. It's like that.
So there is a question in grade assignment, which is I think its question is something.
Okay. Which question?
Question number 6 in grade assignment. It is actually asking minimum vertex cover of graph is equal to 3. But if in the graph, every cover is covered by only 2. Minimum vertex cover is 2 only. So how?
We can take up that thing, but I want you to think about it more.
So can you speak a bit loudly?
Okay, sorry. Now it should be fine.
Yes, sir.
Is
Yes,
it fine?
sir.
Yeah.
Yeah,
Okay.
yeah.
Okay. So I'll start the class, and then we can take up your questions at the end. Okay. So let's start this. So I can see like 26 of you have joined, and we are like 46 of us here, like 40. Yeah, 44 around. So I want all of you to join here, then only you will be able to participate better, because you can test your own time efficiency with me, and we will also discuss the concepts, like not the concepts, but I want all of you to participate here. So I'll just put up the questions, and we all will interact and learn from this. Okay, so that's how it's going to be. It's like kind of interactive one. So let's start with this. So yeah, so those who haven't joined can still join this. You can actually go to joinpd.com, and you can see here at the top right corner, you can see on the of the screen, you can see the code, and you can use that code and join. Okay, so this is like, of course, all of you know it's maths 1 session, so it's on week 10. So myself, Vicky Kumar Sharma. So how is this going to happen? I think all of you know, because week 1 to 4, this was
Yes, sir.
this is how we
We
used to
know.
do, right?
Yes.
So those who were not there, for them at least, this session here, what we do is, like, we give you a question, and then we give like 2 to 5 minutes to solve the questions, and then I ask you to raise your hand, those who want to discuss that concepts, and collectively we discuss at the end, like, what will be the solution what I have, and then we discuss it together. So that's how we do, and we also look at the approaches, like what your colleagues are thinking about that particular question, and is there the smartest way of doing that particular question. Okay, that's how the session goes. So yes, so this is just a screenshot showing that how will the question look like, and you need not submit anything. Whatever you select in these answering options, it just comes to me. Okay, so we can see the response from there. Okay, so this is just a test problem. Here, a simple question: how many vertices are there in the graph? Okay, so I can see like 38 of you are here. So just give the answers, just to see. This is just a test question. So just to see how many of you how you're giving the response, so that we can see actually like whatever you're entering, it comes to me or not, right? So we can see that. Let's see what are the responses. So see, this is how it comes. Well, how many are there? So 3 plus 4, 7. So 7 vertices. So let's see how many of you are saying this. So you see, most of you are giving this answer. So I can see that, so whatever you type or whatever you text, I get the response. This is what it is. Okay. So now let's go to the next one. So before going to the next question, I'll just give you some theory about the question.
Sir, your voice is low, sir.
Yes, sir. Voice sometimes is being so low.
Okay, now is it better?
Yes, sir.
Okay, so fine. So before going to any particular question, I'll just give you a small theory about it, and then we can take up that question, so that it will be a brush up for you as well. Okay. So now there are some facts about the graphs, vertices, and degree. Okay. So these are 3 facts which I have jotted down here. So any vertex in a graph having n vertices can have a maximum possible degree of n minus 1. I think we all of us agree. Okay. And those who do not agree can actually give me, a contradictory example, and then can disprove me here. But I think all of these are like proven facts, and that's why we have jotted it down here and given you here. Okay. And the other fact is, some of the degree of all the vertices will always be even.
Sir, it will be in the case when directed and undirected both. No?
This is for you consider as an undirected graph, but still you do not talk about what like the vertice so when it comes to about like when you talk about this vertices and degree, right? So degree is basically you speak for undirected graphs, right? And it is wrong to say for directed graph you cannot say as a degree there.
Yes.
There is
In degree and out degree.
Yeah, so you have specifications. So when it is just in degree, so it means that we are talking about undirected graphs. Okay. So that is something we'll have to keep it in our mind. Okay. So if 2 vertices in a graph have degree n minus 1, it means there will be no vertex with degree 1. Okay. So understand this. Now let's say if you have five a graph with the 5 vertices, and it has got, let's say there are 2 vertices with degree n minus 1, then that graph will not have any vertex with degree 1. So you have to keep in these mind like these 3 facts, and based on these 3 facts, let's take up the first question. So I'll mute you all. So I'll read out this question to all of you, and you can just start giving me your response. Okay. We have a graph G with vertices A, B, C, D, and E. So you can see that there are 5 vertices. We write down the degree of all the vertices in an order A, B, C, D, E. Which of the following is the possible listing of the degrees? Okay. So take 2 minutes maybe and try to solve this. So you basically have to solve this. You need not wait for, like me to explain this particular solution for this. So you can actually solve with me. That's why this session is, it's solve with us, right? So all of you can take out your pen or whichever writing devices, and you can just practice, just give me the answer, or you can randomly, not randomly, but if you have any other ways of thinking, like what would be the possible option, just think of it. Okay.
Sir, your voice is again.
Okay, now it should be fine. I actually
Yes,
have
yes,
to
yes.
keep this here. Yeah, fine. I'll take care of it now. Okay.
Yes, sir. Done, maybe.
Done. Okay, so whoever has done, I'll
Maybe.
just give you 2 minutes. So at 8:10 we can take up this. So I can, here you can see the time running. So at 8:10 I'll start. Okay. So those who haven't joined this yet, I request you to go to joinpd.com. Just type this joinpd.com and use this code SJJLOF. Okay, and then you shall be able to participate in this session. So you'll be able to answer and all that.
Sir, in week 10, resources from instructor Google Drive link is there, no, sir?
Okay.
In that slide, lecture 8, 9, 10 is not available, sir.
Okay, slides 8, 9, 10 is not available. Lecture slides.
Yes, sir.
I think you get it in that particular week. You have to go with resources from instructor, and then you get, I
Yes,
guess.
sir. In that particular week only, sir. In week 10, resources from instructor week 10.
It's not there, sir.
Okay, so which all weeks?
Only week
Uh,
10, sir.
Only
It's
week 10. Okay,
incomplete. It's
okay, fine,
incomplete.
fine. Okay, it's incomplete basically. Okay, fine. Okay, fine. We'll look into it. So yeah, actually, it will be incomplete because previously this graph theory was of 3-week content, but it has been merged into 2-week contents. So you would see that some of the contents you have the things on your portal, but you will not be asked, like for an example, DAG, right? And the applications of DAG. You would see that there is no questions on practice assignment and graded assignment, but the questions that will be asked in the week 11, these on the basis of this. That's why those are not given here yet. So I think you can check it in week 11. You will get that slides. Okay.
okay. Okay.
Yeah. Okay. So let's start then. Let's see what are the popular responses. So do any of you need more time to solve this? Okay.
No,
Okay, so
sir, we don't need any time.
okay, so let's see what are the popular responses for this particular question. So 17 of you are saying D as the answer, and also A and B. Okay, so I got my response. So most of you are saying D as the answer. So who would like to discuss this particular? You can raise your hand. Maybe. Yeah. So who is it? Aditya?
Yes, sir.
Yes, Aditya.
So, as per the rule that you have discussed just a minute ago, like in the first option we have 2n-1 because we have 5 vertices. So
Okay.
we have 2n-1 is, and when it happens, there will be no one edges with there will
Okay.
be no vertices with one edges. So it
1
is wrong.
degree.
Sorry, 1
degree.
degree. Sorry, I'm so
Yes.
sorry.
Yes.
1 degree.
Okay. Yes.
And
Yes.
in the B option, we have option 2, 4. Like a degree can have one n minus. Sorry, a vertices can have n-1 degree. So it is starting with 2. So there is no point to consider this option.
No, that is incorrect. But I'll discuss why it is incorrect.
Yes, and
Because
okay.
the number is 5, 2, 2, 4, and 7. This is odd. So odd is not possible.
Odd is not possible. It has to have even,
Even.
right?
yes.
That's
Because you
why
remember
B
the
is not
first one.
possible.
And the C option is wrong because if there is n number of vertices, then n number of for any vertices n is not possible as a degree. So, and the D
Right.
option, that's why is right.
Right. Okay. So if there are n vertices, you cannot have n edges. Basically, you can at most have n-1 edges, right? Sorry, n-1 degree of that particular one.
Yes, it is a little bit confusing.
Okay, fine. So then what about D?
D is right because they have even number of degrees, and we have also highest degree is n-1. Like they have 5 vertices, and we can have n-1 as a degree for a vertices for any vertex given vertex, and we can have subsequently 3, 2, 2, 1, and it's also even if you plus all of them. 4 plus 3, 7 to 9 to 11 plus 1 is 12. So that's why it is the right option.
Okay, fine. Let's say you had an option E, okay, and you had the number of degrees given as 2, 2, 2, 2, 2, 2, 2, 2, 2. So would that be an right option?
There is 5 times 2, right?
Yeah.
So 1 second. Actually, I'm not getting it. Yes, it could be possible, I think, because it is an even. So why
It
not?
is an even, and what else? Is it fulfilling the other conditions?
Yes, it's not fulfilling a condition.
Why I asked you is just because here you had this doubt that
Yes,
it should
yes.
had 4, so that's why I asked this question. Okay.
Okay.
So it need not be, okay, need not be that the n-1 degree should be there. compulsorily. It need not be. Okay.
Okay.
All right. So is there any other approach? Like, would anybody else like to discuss this?
Sir, 2 comma 2 5 times possible, right, sir?
Yeah, that is possible. 2 comma 2 comma 2 comma 2 comma 2 is possible.
Yes, sir,
So we
possible. I
need
draw
to
that graph.
note,
That's why
Okay. Okay.
so we need to note down the 3 point in mind, right, sir? That
Right,
previous,
right. These 3 points, if you have, this is enough. Okay.
Sir, I
So
have a question. And I know that is D. It seems so, but why not A?
why not A?
Why not A?
Okay. So look at this.
Any vertex graph having
Sorry. Look at the third one.
2 vertices in a graph have n-1 degree. It means there will be no vertex with degree 1. Can you please explain this thing once, please?
Sir, we can explicitly prove that, no, by drawing the graph.
Okay.
Exactly. You can actually do that by drawing the graph. That's why I have given that as a fact. Like this is a proven fact which you can yourself, like you can draw any number of vertices and you can draw and prove that. So
Okay,
so
sir.
look at this. Now the third statement says what? If two vertices in a graph have degree n-1, n-1 once you have you have a graph with 6 vertices, suppose. So n-1 means what? 5. So now if you have a if you have a graph with 2 vertices with 5 degree, okay, then
Yes.
you will have no vertex with degree 1. This is what it says.
No vertex with degree 1.
Right.
Okay.
So now if you go back to this one, now look at this.
This is the 1 degree.
So you cannot even have one.
Okay.
You cannot have one vertices at all. So that's why this is incorrect. Okay.
Okay. Thank you, sir.
You're welcome. So now, so those who are still struggling to understand this, so for them, let's draw a graph maybe.
Sir, may I?
Yes, please.
So, sir, first we can take a approach. Just now, you last slide you have explained n-1. So we have 5 points. So in that case, what happened? We will minus n-1. That means n is here 5. So 5 minus 1 is 4, right?
Right.
So 4 we have to take first. So that in that case, A will be rejected because it's 4, right? And C will be rejected.
No, why A?
Sorry, A, not A, sir. Sorry. It's C, sir.
Right.
Because
C
it's
will
5.
Be rejected.
Yeah.
Correct.
C will be rejected, and it is always have to be even number, right? So B will be
sum
rejected.
Of the vertices.
Yeah, sum of the vertices will be even, right?
Even, correct.
So in that
Sum
case,
of
B
degree,
will
not
Sum of
vertices.
degrees.
Sum of degree,
yes.
sorry. Sum of degree, yeah.
Yeah. Okay.
So B and C will automatically be rejected.
Exactly.
Now
yes.
it's between A and D.
So now come to A. Now for A, it says, no, you have a statement like if you have a 2 vertices with n-1 degree, then you cannot have any vertices with degree 1. Now you have 2 vertices with degree n-1, right?
Yes.
Then you cannot have any vertices with degree 1. But you can see there are 2 vertices with degree 1.
Degree 1.
So right. That's why even this option is neglected. Right. And that's why, and look at the fourth option, it actually satisfies all the conditions, right? Look at the sum of this, it is even.
Even number.
And now if you don't have 2 n-1 degree, 2 n-1 degree for 2 vertices, right? So even this is ignored. So even that is fulfilled here,
yes.
Right? So all that condition satisfies for D. So this is right.
Sir, there is one more rule. Total number of degrees is 2 times m. M is depending S. That is has been taught in lecture. So that is right.
Come once again.
Actually, in the lecture, Professor Madhavan said that number of degrees will be 2 times m, and m is representing S. So that is right.
Yeah, that is right.
Okay.
You can take it that way as well.
Okay.
So it's you can actually understand that because 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 each vertices, now you have, let's say, two vertices, right? Let's say you have a two vertices, and how many edges do you have? One, right?
Yes.
Yes,
So
sir.
that's automatically like this will have 1 degree and the other will have 1 degree. So it's 2 times 1. So it's like that, right?
Yes.
Okay.
Yes,
So
sir.
now you can see the same explanation is written over here, which you can actually read this.
So, sir, like you told, like if we have the option like 5 times 2,
Hmm.
then it would be also the correct. Can you
Right.
give me the explanation for that?
Okay. So again, I'm claiming that these three are my facts. Okay.
Mm-hmm.
So considering these are like facts and it's right. Okay. So if that is the case, all I have to do is just make sure that what I'm giving in my option is correct as per these facts or not. Okay. So I'm saying 2, 2, 2, it's like 5 times, right?
Yeah.
Right. So any vertices of a graph having a maximum, so any vertex in a graph having an n can have a maximum possible degree of, this is like maximum possible degree, right? But you can have a
Okay.
minimum also, right? So this is okay, fine, it's satisfied. Sum of degree of all the vertices will be always even. So
Yeah.
again, when you add 2 plus 2 plus 2, it's like 5 times, so it's 10, so which is an even. Again, this is fulfilled. If two vertices in a graph have degree n minus 1, well, you don't have n minus 1, so you're not checking for this, right?
Right.
Now
Okay.
if you want to verify by yourself, just try to draw the graph for that. You shall be able to
Sir,
get it.
can you explain the second point with
This one?
with example? Yes, sir. Not
Uh,
understand 2 plus 2.
Okay, so now let's take one example here. So maybe
Yeah.
you can see my screen, right?
No.
Note I have
No.
opened. Okay, just a minute. Okay, so now you see this. So second example was like sum of the degrees will always be even, right? That's what it says. Now let's say this is your vertex 1. Now I'm taking a graph with 3 vertices, suppose. Okay.
Yes.
How many edges do I have?
3.
So 3, sir.
Let's say I have 3 edges. Now these are 3, but it appears what like these are 3 edges, but we are getting confused where in the edges and the number of degrees, right? These are two different things. Though edges are how much?
3.
But
3.
how many? What are the total sum of degrees? Total sum of degrees of all edges?
6.
6, sir.
Sir.
Okay.
6,
So what is the degree of 1?
2.
2.
Degree of 2?
2.
Sir, here
Degree of 3?
2 again.
So altogether it is 6. So it's even like that.
So the reason for that is that every edge presenting degree of 2. So that's why it is the reason that every graph has even number of degrees.
Actually, if you are to ask me, the reason is what somebody pointed out, saying that Professor Madhavan once told that the total number of degrees, right? The total number of degrees of that particular graph will be twice the number of edges, right? So twice the number of edges is what it will always give you an even number.
Yes, anything you multiply with 2.
Right. So that will always give you an even.
Yeah.
Right.
Yes. Right.
From that fact, actually, this has been written. Okay. So I hope this is okay to all of us now. Fine. Okay, clear. So if that is okay.
Explain the third condition, sir.
On the third condition. So third condition is this, right? If two vertices in a graph have degree n minus 1, it means that there will be no vertex with degree. Okay, just let's take a simple example again. Okay?
So can I explain? Can I try?
Please go ahead.
So if a vertex has degree n minus 1, that means that vertex is connected to all other vertices.
Right.
And if you have two such vertex, then that means that each vertex is at least connected to those two vertices. So therefore, the degree can never be less, can never be 1.
I mean, it's perfectly right. So did you understood? You understood? The person who asked?
No, sir, can you show it with some examples?
You understood? you want me to show with some examples? Well, that was really nice explanation what you gave. So let's take one example, or let's go with this. Okay, so maybe I can take 4 degree this time.
Sir, show it in a show it diagrammatically, sir. Otherwise, you will not understand.
Correct. 1, 2, 3, and 4. So now let's do this. What is the maximum degree for 1? I mean, if it is like, now look at this. Now, if it is your vertex 1, so how many vertices do we have for this graph?
4.
4. So what is the maximum possible degree of vertices can have? 4 minus 1.
Yes.
3. So this will have 3. Now again, this can have 3. Right?
Yes.
Now 3 has 3 now. 1, 2, 3, and 4 also has 1, 2, 3. So well, now okay. So here, look at this. Now if this has 3 degree and this has 3 degree, right? Can you think of any other vertices with 1 degree?
No.
Okay, well, this is like I have given you. Maybe I can take up a larger vertices and then explain you this. A graph with the larger vertices and explain you this.
Yes, sir. It is reasonable. You can understand.
You can understand that, right? So let's say all of these have degree 1. Okay, so now if you look at that way, so this is degree 1. This has degree 1. This has degree 1. This has no degree. So if you want to connect this, so you will have to do this, right? So if you want to make this connected graph, so at least this is what you will get, right? Now I want to create how many? Like I have to create n minus 1 degree. So this is 5, right? So I must have what? 4. So now what? Let's say 1 has 4 degrees, right? So this is 1, 2, 3, and 4. Now what do you see? This has got 4 degrees. Now how many degrees it has? 4. Now let me say now I'm trying to connect. Now at this point itself, if you see, like, you have, but you see that if I don't had this, now can this be like, let's say you had a graph like this, okay? You had a graph like this. Now you have a vertices 2 with degree 1, right? Right? Now let's create, now think of the other vertices which has got, a degree same as 1, which is 4, right? So now if you try to do that, so what, now you will connect this with this. So this is going to be 1. Now how many it has got? What is its degree?
3.
Well, this was connected already, so I was connecting it again. Now look at this and this. So it has to go and meet there. Now what, can you think of any vertices which can have, like degree 1? You actually cannot think of, right? So if I have to do this, now you might say like, okay, remove this. Even if I remove this, I'm not violating this, like it has degree 4 and this has degree 4. If I'm not violating these, and then if I look into this graph, now look at this. Can I remove any other vertices so that, the degree of 1 is not violated and degree of 3 is not violated?
No, sir.
You cannot think of, right? So this is how you can think. This is one other way of telling it, but this is actually more complicated way of saying it. What someone, I don't know, what was his name?
Archit.
Yeah, Archit. Yeah. So what Archit explained was, it was very straightforward. But I hope you understood by this. That's perfectly fine. Like however you understand. Is it clear?
Yes, sir.
Now it is clear. Okay, no problem. So now let's go with our next question. So the solution is basically the same thing. It's just the sentence has been reiterated and been told here. Okay. And you have been given graphs for each of this, so you can actually see this later on. Now let's go with the next concept. So I'll just discuss this concept again. What is basically adjacency matrix? Okay. So it's basically, adjacency matrix is a matrix. Okay. So you know what matrix is? Matrix will have a rows and columns. Okay. So over here, adjacency matrix is basically a matrix with rows and columns labeled with the graph vertices. So it is what? It is labeled with the graph vertices, and all entries in it are either 1 or 0. Okay, so this is what adjacency matrix is. So first of all, you are representing a graph vertices, right? So each rows and a column represent the graph vertices of that particular graph, and the entries can either be 1 or 0. Okay. So now how do you assign 1 and how do you assign 0? So basically, if a graph is given to you, and if it shares an edge, then you will give 1. And if it does not share any edge, then you will give 0. For an example, look at this graph. Now, how many vertices it has? How
5.
many?
5, sir.
So 5.
5, sir.
So now this this graph has 5 vertices. Now what? Now how will you draw the adjacency matrix for this? So this is how it's going to be. So let's see how. So now first of all, now recall what we studied just now. Now it is adjacency matrix is a matrix which represents what? Rows and columns labeled with graph vertices. So you can see this. These are what? Graph vertices. You can see here, right? The rows and columns are representing the vertices of that particular graph, and the entries, as you can see, it is 1 or 0. Now I'm saying that if I and J, let's say A and B, if shares an edge,
Then 1.
we'll assign 1. So now A and B sharing an edge, so you will assign 1. Likewise, since this is an undirected graph, so then you can say B and A is also sharing an edge, right?
Yes, sir.
So B, A is also given 1, right? So all you can do is you can just build this upper triangle, and just upper triangle in the sense, consider this diagonal element.
Diagonal is 0.
So diagonal will be 0, that is for sure. But what I'm trying to say is diagonal elements, and I'm telling above this is one triangle.
Just like sir,
element,
C and D will be 0, sir.
Right. So likewise, if you look at BC, so B and C is given what?
1.
Right? Now look at this. Just look at this. B and E is given 0. It indicates what? There is no edge there, right? So
Yes.
let's backtrace and see. Now B and E, does it shares an edge? No.
No, sir.
That's why it was given 0. So like this, you can look for any other edges, right? So now from E to E, now okay, E to E, I'm saying whether, now let's look at whether we have an edge in E to D or not. So you see that E to D, there is no edge, so it has been given 0. So now let's look at our graph. Is it that? Yeah, so it's basically there is no edge. So it's just likewise. Now if I have been given an adjacency matrix and I ask you to draw the graph, you can actually draw the graph, right?
Yes, sir.
And also if I give you an a graph and I ask you to draw the adjacency matrix, it's easy to draw, right? All you have to draw is just find out this and just replicate it at the bottom. That's all. Now this is just the symmetry. Look at this. Symmetrical, right? So I hope you understand this.
Yes, sir.
Now having known this, now answer this question. The maximum number of non-zero entries in an adjacency matrix of a simple graph having 5 vertices can be. So without telling answer, just start giving your response, and do not post your answers in the chat window. Okay, so I'll mute you all and I'll give you 2 minutes. So some of you are asking how to find vertex cover independent set. Okay. I hope this was discussed in the previous session, and I believe this DAG was not discussed, right? So longest path is something not discussed. We'll see if we have time, we'll discuss. Else we can also discuss in the week 11, because that is where you have been asked questions. So we'll see how it is. Okay. But you must know what is vertex cover and independent set before itself. So Rishabh, did you attend the previous session?
Done, sir.
Done?
No, sir, I didn't attend the previous session.
We can just take a look at it because it has been explained nicely. But
Okay.
still, yeah. And I think we'll give you the timestamp also. I think
I also didn't attend the last session.
Oh, you didn't attend, so that's fine. So what we'll do is we'll just provide you the timestamp for that video, so that you know, and also the description for that timestamp, so that you can actually click and just see that part. Okay.
Okay.
So that you will not waste your time. And also we'll see if we have time at the end, we can just discuss that concept. That's
okay, sir.
Okay.
Okay.
So fine.
Thank you.
Yeah, you're welcome. So now let's see how many of you. Now I can see like 50% of you have given answers already. So Okay, we'll see that. The maximum, so the question was very clear. The maximum number of non-zero entries in an adjacency matrix of a simple graph having 5 vertices can be. So they are asking non-zero entries, maximum number. Okay. So now what are the popular answers? Let's see. So some of you are saying 25 and most of you are saying answer as D. So let's see what is the answer for this. Okay, so who would like to discuss this? Ajri, you want to discuss?
Yes, sir. The total number of the adjacent matrix, the numbers are 25 because 5 into 5, 25, and all the diagonals are 0. So that 5 diagonals are 5 numbers are 0. So 25 minus 5 is equal to 20.
Right. Yeah. So that's what the explanation is. So do any of you can think of any other thing?
Actually, sir, in this question we can say that vertices cannot be self loop, like it cannot be connected to self. That's why it is 0. So if we draw the graph of this matrix, so 1, 2, 3, 4, 5, so one cannot be connected with itself also. So that's why it is 20.
Okay. So that's the other way of saying why diagonal elements are 0, right?
Yes, all primary diagonal.
So, sir, what is the correct answer for this one? 20?
Yeah, 20.
Okay, okay.
So you see that, do you have any other answers, like any other thing? Can any of you?
Use There
you-
is one theory. What is the number of n into n minus 1, where n belongs to number of vertices.
Okay, so you know what? Actually, that is also right. It's just because. But again, how did you come to that conclusion that it has to be n into n minus 1?
Sir, a vertex can only be connected to n minus 1 vertices. So for each vertex, n, so it will become n into n minus 1.
Right. So basically, it's a complete graph, you can say, right? So wherein all the vertices are connected with all other vertices, right? That is the condition where you can have the maximum entries in your adjacency matrix, right? So if you can maximum have how many vertices? Sorry, if you have, like, let's say n vertices, then what is the maximum number of vertices degree that you can have for each vertex? N minus 1. So that's why it is n into n minus 1. Okay, so that's what I was looking for answers. So okay, fine. So that is also right. So I hope like we got some one or two approaches, maybe we can say. So that is nice that we discuss something. Okay, so let's look at some, some other solution what we have. So as I was telling you, and what Kajri also told, that was also like, if you can just think of like, yeah, that is what the adjacency matrix is. All you have to do is just remove the diagonal elements and it's done. Now you see that when can you have the maximum edges in a graph? When all the vertices are connected among themselves. Basically, it's like complete graph, right? Complete graph in the sense, all the vertices. Now look at this A. What is the degree of A? 4. What is the degree of B? 4. What is the degree of C? 4. What is the degree of E? 4. D? 4 again, right? So this is the condition where all of them are connected to all of them, right? So how many vertices do we have? 5. And the degree for each is how much?
4.
5 into 4 is what?
20.
This is one way of looking at. Okay, so this is
another way to solve. Nice.
Yes. So now what even Kajri Saha was also telling is the same thing. Basically, if all of them are connected, then all will have what? 1, 1, 1, 1, except this diagonal elements. Right?
Yes.
But when will this eventually happen? When this is happening, right? When all of them are connected to all of them, right?
Yes.
So it's just that we got a bit better picture now. Okay. So now do any of you have doubt here?
It was given that the graph is simple graph. If it is just a normal graph, then can we have 25 elements?
So what do you mean by normal graphs?
I mean, what I mean is the question said that the graph is a simple graph. That means there is no loop and anything like that. But if the question was like the maximum number of non-zero entries in an adjacency matrix of a graph, so can we have then 25? Because that does not restrict the self loop.
Again, you can say that, but self loop, mostly we ignore it, right? I mean,
Sir, your voice is again low.
Okay, now it should be fine. So when it is simple graph, yeah, of course, in Professor Madhavan's video, you would have seen that professor saying that simple graphs is one without the self loop, right?
Yes, sir.
Right. So that is one thing. And usually when you say a graph, you actually ignore that part. You don't consider that self looping thing.
Okay.
So that is the other way looking at it. Okay. So
So
even if it,
this we can assume for this course itself, right? Like we will
yes,
only
yes, yes, yes,
consider the
yes.
simple graph.
Yes, yes,
Okay.
yes.
Okay.
Yes.
Self loop is considered as work, not the edge between.
Right,
Yes,
right. You cannot
right.
actually consider that. But yeah, and okay, that is one way of looking at it. But when you have a directed graph, right? And let's say you have a two vertices, A is being connected to B and B is being connected to A. Like you have been directed to this. You consider as two different edges at that point of time. And you have the concept of cycle at that point of time. But you cannot have it right away for this kind of things. So those are things that we can, discuss in the later courses. But for time being, this is fine. When we simply ask you graph, forget about the looping and all that. Okay, it will be just a simple graph. Okay.
So then for directed graph also the answer will be 20 only, sir.
Like again, but we are talking about adjacency matrix for like undirected graphs. That we will see later on. No worries.
Okay.
So again, it's basically the same thing. So, the answer is 20 for this. So we discussed this already. So now let's discuss some questions on BFS tree. Okay. So what do we really mean by BFS tree? So actually we have gone through, I assume now it's like, tomorrow you have your assignment submission. So I can also understand that's not counted for grading. So it's fine. So BFS tree, so original graph, and it's, and I think you have done some kind of calculation on this, like on
Yes.
this BFS tree.
Yes.
So if you have been given a graph, like some graph, then, and you are asked to find out to draw the BFS tree, so you can actually do this. I can assume that you can do that now. Okay. Likewise, if you have been given a graph and then you are asked to find out the DFS tree, I assume that you can do that. Okay.
Yes.
So now over here, I would just tell you, like, if you have if you have been given a graph and the BFS tree is drawn for it, then what is some observation that we have to take from this? Okay. So now notice this, which is mentioned here, 3 points. Now, both the vertices at level I in BFS tree. So level I means what? If this is level 0, this is level 1, this is level 2, and this is level 3, right? So this is what? So level I means I starts with 0 to n minus 1, let's say. Okay. So both the vertices at level I, So both the vertices at level I in the BFS tree may be connected by an edge in the original undirected graph. So this is one key point that you have to take from this. Okay. For an example, look at this tree A, B, F. Okay. Now look at this. B and F are connected, right? In the original graph.
Yes.
But in your BFS tree, it is not connected. So look at this statement when it says both the vertices at level I in BFS tree may be connected by an edge in the original undirected graph, which is a right statement, right? Agree? Agree? Any doubt
Yes,
here?
sir. Yes,
Okay.
sir.
So that means you can basically have an edge in your, now I'm coming from here to here. Now, if I have given a BFS tree and I ask you to find out, can you have an edge between B and F in your original graph? The answer will be yes, because at the same level, you can have an edges in your original graph. Okay. I hope that is okay. Also,
Yes,
from the second point, what we can take is from the level I and level I plus 1, you may still have an edge in your original undirected graph. That means you can actually think of that your original graph might have an edge between FC. Okay. So that is one thing that you can think of. Okay, though it is not given here, but you can think of that there might be, because over here see, if I had to just connect this and then draw the BFS tree, you would find that it might have in this original graph, though it is not there for this graph. But when I simply give you this BFS tree and I ask you, can the original graph have an edge between F and C? The answer will be yes.
Yes.
Because you can have an edge from at the ith level, and you can also have the edge from I to I plus 1 level. Okay, but you cannot have a vertices in your original graph at a higher at the higher degree, at the higher levels, that is I plus 2 level or above. Okay, so at most what you can have the edges in your same level or one level above, or let's say below, but you cannot have more than that. You cannot think of like I plus 2 or I minus 2, essentially that thing. Okay, so I hope this is clear. Did you get any idea about it?
Yes, sir.
Okay, so if you got some idea, let's discuss one question, and don't worry if you didn't get any idea, I might discuss one question to you wherein we can actually think of like how is this happening. Okay, so now I just told you about BFS tree, and assuming that you have seen the video lectures and attempted some of the question and the previous live sessions, what about
Yes.
the DFS tree? Can you talk similar? Like, can you have, when the DFS tree is given, what kind of edges are allowed in your, in your original graphs maybe? Okay, so what about DFS tree? Can somebody tell me?
Yeah, this is also possible for DFS tree, except cross edge is not possible in DFS.
With
Cross
different
edge?
branches.
Cross edge is
between-
possible. Cross edge is
Have the edge
possible.
between the branches.
Between the branches,
They must be in the
not
same
possible.
branch.
Right.
Yeah.
Right.
Has to be
They
in the
must be in
same
the
branch,
same
but
branch.
in BFS, cross is possible, not in DFS.
In DFS, you cannot have edges in the cross branch. Okay, but you can have on the same branch at any level, right? So you
Yes, at
are at
any
0
level.
level, but you can still have an edge connecting your, let's say, 5th level or 6th level or so. Okay, so that is
Yes.
allowed in DFS tree.
Oh.
Okay, so having known that, so it's basically the same thing. So DFS tree for an undirected graph can only have edges in the same branch. So you must make a note of this, because if there is an edge between the two vertices of a different branches, then the neighbors of the vertex must be visited in order to remove from the stack. So it's just that what you would have seen in the lecture, professor was actually telling you how is this stack being built up, right? And then you remove each stack, right? So if they are on the same tree, I mean, if they are on this different branch, if they are if they are on the different branches, let's say the different branches are connected, so eventually what you will go through the you will build up your stacks more, right? And it will become the part of the main branch, in fact, right? So you will not have two branches in that case. Understood? So it's just that, and because of that these things has come out. Okay, so now based on these informations, now look at this. Suppose we obtain the following BFS tree rooted at node A for an
Previous slide,
undirected.
just I wanted to make a note of that. First statement.
Which one?
Yes, sir. The next one. Yes, yes. Edges in the same branch. Okay, okay, yes.
It's
I
basically the same thing. I think I have, I have just copied the same slide again. That's why I skipped it at that point. Okay, so now let's see. There's a question 2 now. So suppose, essentially, I think this is question 3. Suppose we obtain the following BFS tree rooted at node A for an undirected graph with vertices. There are so many vertices: A, B, C, I think up to J. K, L, M. There are so many, but yeah, there are so many vertices. Which of the following cannot possibly be an edge in the original graph? Okay, so this is the question.
Done, sir.
Done. So actually, on the basis of fact what we have discussed, I want all of you to take 2 minutes and think about this. Like, yeah, what could be the right answer? So all those who got it, just maybe you can just read something else, or just bear with us for 2 more minutes.
Done, sir.
Okay. So maybe at 8:50 we'll discuss the solution for this. So all of you can just wait for 2 minutes, or if somebody is doing and you need time, you can tell me. If you don't need time, we can just discuss the solution. Do any of you need time to solve this?
No.
No, sir.
Yes, sir.
Okay, then we can wait. If there is one more, we can
Yes,
wait
sir.
actually. Yes, because we should give at least 2 minutes. So do you need some more time?
No, sir.
Okay, fine. So we can just go ahead and discuss this. So let's see what are the popular responses. Okay. Most of you are saying option as C. Some of you are also giving answer as B. Okay, so I'll mute you all.
But sir, I want to understand.
So somebody was telling you want to understand what?
Yes, sir. How this answer came just in short.
Okay. Okay. Okay, fine. Right, right. So you see this, we are talking about BFS tree and we are asking whether, which of the following cannot be possibly an edge in the original graph. Right. So
Yes.
I discussed some of the facts. I told you that in your original graph, you can actually have edges at the same level. That
Same
means
level,
what?
yes.
You can have edges between C and B. You can have edges
Yes.
between CD.
C and
You can
D.
also have edges between FK. You can
Yes.
also have edges between KN, right?
Yes.
So that is, they are on the same level. And you can
Yes.
also have edges one level above or below. So essentially
Okay.
what it meant to say is you can have edge. Now look at this. If this was at 0 level, this is 1 and 2. So this is at 3. So you can have edge between 2 and 3. You can have edge between C and F, but you cannot have edge between C and M.
Okay.
Because what is the level for this? 1, K as level 2, and this as level 3, right? So so what is the difference? It's more than 1,
Okay.
right? So at most what you can have is
More than-
1. So 0 and 1 level you are allowed. I mean, it's wrong to say 0 and 1 because I'm specifying it on the same level or the level I plus 1. Okay, so that is only allowed, not more than that. Okay, so likewise, I cannot have an edge between C and J.
Yes.
Right? So that is what,
Yes.
and because of that particular reason, we see that now let's look at B and K. BK. So what is B? B and K. So this is allowed.
Just one level below. Yeah.
So this is allowed. And what we are asking, which cannot be allowed,
Cannot.
right? So this is allowed. Okay. What about MN? MN is again one level difference, right? So this is also allowed. What about EI? So where is E? E is here and I is here. So it's like 2 level difference. So I cannot have this. So well, this is right. C is right. And what about D? E comma H. So what? E is here and H is H is one level above. So again, this is allowed. So only C is not allowed here, right?
Yes.
Right. So this is the only thing which is not allowed. All right. So now having known this, like, do you have any doubt here? Anybody?
No, sir.
So I think I discussed this. So now it's basically the same thing which is explained here again. You can actually see this part later on. But if you don't have doubt, we can just leave that part. Okay. So now let's go to the next concept. Vertex coloring of a graph. So do you face any difficulty in from graph to drawing BFS tree and DFS tree? Do you have any difficulties in that?
No, sir.
No, sir.
You can actually draw that,
Yes.
Yes, sir.
right? Anybody with
Yes,
no
sir.
answer? Okay, fine. So I assume that all of you know then. So now let's discuss this question, this particular. So since we are following this pattern, that whenever we are discussing any question, so we are following with, we are discussing some concepts of it, right? So now vertex coloring of a graph. So all of us know what is vertex coloring, I assume that. So now
Yes,
having known that, so now again, then what it is, I'll just tell you. Now what do you do in vertex coloring is find the minimum number of colors required to color all the vertices of the given graph such that no two adjacent vertices have the same color. So this is the only rule it has. Now what you will do is you will minimize this. You have to choose minimum number of colors to color these vertices, and all you have to make sure that no two adjacent vertices have the same color. That means I cannot have color between, if I give red color to A, I cannot give red color to C. You understand, right?
Yes.
Because this is the only condition that you have to follow here. No two adjacent vertices will have the same color, right? So if I give red to this, C cannot be given red color. And also I have to make sure it is a minimum coloring, right? So let's color this graph then. So if I give, so what do you do when you do this coloring problem? So we choose one color, maybe let's say we choose red color, and then we assign the color. So now look at this. When I give color A, when I give red color to A, I cannot give it to C and D.
Yeah.
Because they are connected. I cannot give the red color to them. So I just leave that for time being. But I can give it to E because they are not directly connected.
Yes.
A and E are not directly connected, so I can give it to E. But since I have given to E, I have to make sure that I'm not giving to C, F, and R. Right?
Yes.
In that case, I can give it to D. Can I give it to D?
Yes.
I cannot give it to D because A is connected to D.
Yeah, right.
Right? So I cannot give it to D as well. Right? So think it in that way, sense. Because if I have given red to this, and now if I'm saying that this is not connected to this, I cannot just give it to this because I have to make sure that even this does not violate, right? So now what? Now let's say if I'm done with this, now I just made sure that I cannot give the red color to these three things, that is C, F, and H. Now what about G? I can give it to G because neither A is directly connected to G, neither E is directly connected to C. I'm free to give this red color to this, right? Likewise, now if I give it to G, I cannot give the same color to F and D, right? But I can give it to J because you see this, J is not directly connected to E, neither it is connected to G, neither it is connected to A. So I can just give this red color to J. But note one thing, can I give red color to F?
No.
No. Why? Because
it is directly connected.
Also, it is connected to E and G, right? So I cannot give it to this, right? So what about H? I cannot give because of the same reason, right? And also I cannot give the red color to B because again it is directly connected, right? So then what?
But here P and P have the same colors, and both are connected.
Who? Which one?
B and P.
B and
P, bottom.
Okay, that is something we are just giving red colors to everything.
Okay.
That's why we did not give it. Okay, so now I can give it to Q. So if I give it to Q, then I cannot give it to H and I cannot give it to B, right?
Yeah.
And also I cannot assign any color to P.
Yes.
But you see that I can now, as he pointed out, B and F are being white. That means I have to choose different, right? So now you see this, I can leave it as in white, but still let's go with the next color. Now what? Let's say we are choosing green color. Okay. So now what? Now if I give, now I'm free to give C a green color, because you notice this. I'm definitely, I'm not violating the first condition. What it says, the condition is if two vertices are connected, they will not be given the same color, right? So they are connected, right? And they have been given a different color, so that's fine, right? So now C and D can be given a same color. It's just because they are not connected, right?
Yes.
Can I give green to F?
No.
No, it's just because it is directly connected with this. I can give it to H, right? If I give it to H, what about, can I give it to B?
No.
I cannot give it to B. So I can just give it to P, because if I give it to P, I still cannot give it to B, but the other one is red, so that's okay, fine.
But sir, we can give it to B and not to P. That can be done?
No, but H is connected, no? See?
Oh, okay. Yes.
Right? So you cannot do that. So that is not allowed then, right? So, okay. So now we are done with this. Now, what could be now we just have to put one next color. Maybe we can just give it as a blue. So if I give it blue to this, what about, is it violating any conditions? No. And I can give it to, so how many colors we choose?
3.
So let's say it was not blue, but rather yellow. So how many? With 3 coloring, I covered all the vertices, and I also made sure that no 2 vertices has been given the same color, right? So this is what the coloring of a graph concept is all about. Okay. So now, having known this, now we understood something. I want you to answer this particular question. So now look at this. A company manufactures 10 chemicals. Certain pairs of these chemicals are incompatible and would cause an explosion if brought into contact with each other. Below graph shows the incompatibility of the chemical, which is not shown. I'll show it in the next slide. Each vertex represents the chemical, and each edge between a pair of a chemical represents those two chemicals are incompatible. That means if they share an edge, they are incompatible. Okay, so they cannot be stored in the same container, maybe, right? As a precautionary measure, a company wishes to partition its warehouses into compartments, and store incompatible chemicals in a different compartment. So it's not we are actually using a different compartments. It's not the vessels, but the compartments. Okay. So basically, here is the graph for you. Now this represents now compartments. Now what is the least number of compartments into which the warehouses would be partitioned? So as you have read in the question, this vertices represents what? A type of chemicals, and if they are connected by an edges, it causes explosions, right? Now you have to keep it in a different warehouses, or you have to keep it in a different compartments, right, such that there is no explosion, right? So then what would be, how many compartments do you need altogether? And you have to find out the least number of compartments. Okay. So one hint is given to you here. You have to color the vertices in the graph so that no two adjacent vertices get the same color. Okay. So this is one hint given to you. I want all of you to try this question and maybe take some, let's say 2 to 3 minutes. Let's say we're giving you 2 minutes. So at 9:03 we'll discuss this.
Sir, hello. Am I audible?
Yes, yes.
Yes, sir. Actually, I have problems in the graph of DFS and PFS. When you were asking, actually, I could not unmute myself.
Okay.
In the activity question, like after that session, when it gets over, yeah.
Sure, we can discuss that. Or maybe
Yeah.
I'll discuss one question to you. I'll take a very big graph and then I'll discuss to you over there. And I think it'll become easy. Then the activity questions will be very easy. Okay.
The sequence I can check, but when the graph is given, then I was supposed to tell whether it is DFS or PFS, or whether I have to choose among these 4 options which one is correct for BFS or DFS. Then I could not find.
Okay, fine. We can take a look at it. Okay.
Thank you.
Yeah.
Thank you.
Sir, options we have to write like F, B, something like that. F, F, comma B.
You have to actually enter the value here.
Okay.
Okay, no, not enter the value. You have to write the response here. Basically, you have to enter some value. So what is the least number of compartments into which the warehouses should be partitioned? Okay. So that's something you have to say.
It's a graded question.
There is graded question.
Okay.
The graph is different.
Slightly different. Though.
Not the same. Slightly different.
Okay. Do any of you need more time?
No.
Yes.
Anybody?
Yes, sir.
Okay. So
Yes,
maybe
sir.
you can take another minute. Yeah, 2 more minutes. Maybe we'll start at 9:05.
Sir, what is the weightage for the same term, sir? The graph.
Okay, like weightage and all. So see, week 9, 10, and 11 we did not ask, right? So we have the highest weightage. Highest weightage in the sense more questions will be asked on this, but it does not mean that you will ignore the week 1 and week 2 because there are direct questions from all the weeks.
Done, sir.
Sir, this previous question someone asked, right? The weightage in the from the different topic. Could you please repeat the answer? Actually, I didn't get that.
Oh, actually, I mean, we were thinking to, formally tell that what will be the weightage so that, you can actually prepare for your exams. We'll see how we are announcing it. But just to tell you that since whichever was not asked, like, that week 9, 10 and 11 was not asked, right? So that will have the highest weightage. Highest weightage in the sense it will have more questions. That's what it means. But essentially, it does not mean like, it's like 50% of questions being asked from there. It's not like that. But if let's say if we are giving like, if there are 11 weeks and like, if I have to divide it eventually, so somewhat like roughly 9 or something, 9% per week it falls, right? So it will not be like that, but it will have, somewhat like the more questions being asked from here. So it will be like, like somewhat like 15% or something or 20% from these parts. So you really have to pay attention to your week 9, 10, 11. But again, calculus and graph theory are very important. It's really important. That's what I would say. And it's not just week 9, it's a whole calculus and your graph theory. Actually, you guys did not perform well in your quiz 2. I mean, the result was actually very bad.
Yes,
only
sir.
26%.
Very small mistake we had.
26% of you passed.
Sir, I am really
small
scared of the
mistake.
sequence. I am really scared of the sequence. Sir. The calculus part is fine, but the sequence I
Sequence
find
part.
it very tough.
See, whatever is being provided to you, right? Just focus on that. That is more than enough.
Actually,
and learn
sir,
from
the
each
paper
question.
was not difficult at first sight, but very minor mistakes we
Hmm.
have done in between during calculation, or we missed few steps and just come up with some different answer, which is
It's
also.
the MSQ question are very high marks. If we got one option wrong, the whole
Yeah, so we actually took this
right,
feedback.
right.
Last time we had this discussion, right? I mean, we all of us were discussing with you, and we took this feedback because there were questions like which is of 7 marks, 6 marks like this. The questions were there, but yes.
Yeah.
But you see, actually, there were concepts too, and I don't know when we were looking into your answers, it was so surprising that like if you're very sure about, there were students, I don't know why they chose it like this. If say there are 3 correct, if you're very certain about 2, then I don't know, like why do you go for wrong options then? And if it is like a very high marks question, right?
No, sir. Actually, if there are 3 options are right, and if we choose one option which are incorrect, then the total marks will go.
That's what I was saying.
Yes,
That's
that's
what I'm
why
saying.
we got very low marks, sir, actually.
Yeah.
That is what the whole thing is about MSQ, no?
Yes, sir. Yes, sir.
Right.
But the options are so much of
But you should
confusing,
be
sir.
smart here in way, because if you see if it is of 7 marks and you are very certain that 2 options are being right, I would not take the 3rd option. I will like
Yes.
fine.
Sir, actually, I did the same in quiz 1, sir. But what actually went is, I got only half of the mark. So I thought this time, okay, we will opt for more options. But this time also I got very less marks only, sir.
Yeah. So actually
So
we
what
had
I
this
think was
discussion
that
with.
the questions were very easy, but most of us made
Yes,
very,
exactly.
very, very critical silly mistakes.
Yes, exactly.
The questions are very easy, but answers are very tough. Sir.
Yes, sir. The options are
Not
really
tough.
very confusing.
Yeah, very
And
confusing. We would
one more
feel,
thing, sir.
yeah,
Sin
this
x
kind
by
of
x, careless mistakes also. I thought
Yeah,
it is
that's
1,
what.
but it is
Yes,
0.
It is
Yeah.
0.
Later I
Yes,
realized.
exactly.
Yeah,
I
we
too
thought
lost
of
mark
giving
for
partial
that.
marks there, but we were like,
Yeah.
That sum and all is
Yeah.
really very
you
easy,
should
sir,
actually
actually.
understand
Yes,
what is, and there were instances where you should actually understand what is sequence and what is a function thing, right? So you really have to understand this. Well, I can understand you didn't have much time and all that.
Sir, but marks got updated today.
It's updated already.
Yeah.
Yes,
Yes,
it is
sir, yes,
updated, sir.
It's
Yesterday.
So you can
updated.
see your marks. I don't know how
Yes,
did you
In
do,
the
but
dashboard, in the dashboard it is. In the
Yes, it
dashboard
will
it is.
exist topic.
Oh, I
Sir,
So,
all
you know,
the
like-
NET
need to
type
check.
question
I
was
have not
easy,
yet.
but MSQ was very tough. NET was very easy. All questions.
Yeah, but if you are to ask me, all the batches, like the previous batches, they were like NAT questions are tough, not the MSQs. There's like the first batch where I can totally understand there were no questions before of 7 marks MSQ, but this
Yeah.
time it was, so that's why this thing is.
So the
coming.
NET question was very straightforward. Like if we
Yeah.
know the concept, we can answer. But in MSQ, even we know the thing, but in one option out of 4, we don't have any idea like how to calculate the things.
Yeah.
Sir,
And you
but,
know,
no, sir, but from previous, previous terms, sir, this term question paper is a little bit tough. Because I have solved the previous term paper also.
Yeah.
So I have I compared. When I compared, I find out that this term is a little bit tougher than the
actually
last.
set 2 we made tough. I mean, quiz 2 we made slightly tough. It's just because, you know, we wanted everyone new to focus in your end term, because that's where you score more, and you know, your thing is like that.
Yes,
Sir,
yes.
while
So
while
that was also
revision,
there.
Sir, that time we have also college exams.
Yeah.
Sir,
Actually, we
Whenever
were.
I see the MSQ question, I don't know. I got so many I was so nervous that I couldn't attempt that MSQ type question.
Okay, but you should be like kind of happy this time, because the highest marks is 4. So even if you have for questions, you know, actually we prepared already the question paper, and then we had discussion when we saw your result. We were like, you know, we internally meet, we all teams, like let's say stat, CT, and maths and other higher courses, and it's like you know, like maths always, it's, you know, it turns out to be, but everybody thinks like, yeah, fine. You know,
The
maths
highest
actually goes
highest
well.
marks is how much? 4.
Highest marks
No,
is
no.
about 90 only. So there are students like very like five of you who have scored above 90 in quiz 2. So there are some, yeah. All right. So now let's discuss this. But yes, we can discuss more all of these in the end term when we are doing revision, and then you will have a clear idea on that time, right? So yes. So let's come to our thing here. So now on this particular question, so let's see what are the popular responses for this first, and then we can go at the answers. So most of you are saying 4, 4, 4, 3, 5. Well, you cannot have 5.
3, I think 3 is the right.
So at most you can have is 4 colors, because if you would have gone through
3
the
is the
lecture,
right
you would have
answer,
understood. 3 is the right answer. People giving answer as 6 as well. Okay, so 3 is the right answer. So let's see. Maybe any of you can raise your hand, and then we can discuss. Anybody? Please raise your hand.
That's 3.
Yeah, the answer is 3. Who is this?
No, I didn't. I did it 4.
Okay, you got it 4. So
It's
let's see
4.
what.
Yes, sir. My answer is also 4.
Okay, so let's
Because
see what.
A, C, E, D, this
Fine,
all
fine, fine.
4
Yes.
are connected.
Just a
So
minute,
if you're doing 3, it's not possible. Then D is going to be same color.
Yes,
So
the
A,
answer
C,
is
E,
4.
D has to be 4 different colors.
Okay, so fine. Let's see. Like those who are getting 3 as the answer, maybe Biplab.
Yeah.
Yeah.
I will try first time, sir. Okay. So
that's okay. Yes.
Yeah. Competition is in the different level, time and other things.
Mm-hmm.
So the approach what I have taken, just seen like how you were doing the coloring.
Yes.
So first I tried to color the maximum number of vertex with the same color.
Okay.
So what I have done is, F is in red, then I is in red, then E is in red, and A is in red. Okay. After that, I went.
Okay.
Why E?
Yeah, why E? E is directly connected to A, right?
A or E.
That can't be.
Okay. I think coloring
can't
of
be,
E
sir.
is in red is
The basic
incorrect.
thing is
Okay.
in that A, C, D, E. This
then
all
A,
are connected.
then
So it
H.
has to be 4 colors. Then
Sir,
we
F.
distribute 4 color
Only
outside.
F, A,
4
and H
is
Sir,
can be
F,
the
A,
same
and
color.
I, sir.
Okay.
4 is the answer.
Who is telling
H
me
or
this
I,
F?
yeah.
Just a minute. Yes. What F is what?
The source node.
Okay, fine. So maybe just let's look into this and then we can discuss. So let's go with the coloring red. Okay, so if I'm giving red color,
Sir,
so
I have done the same, sir.
Okay.
F A and I, F A and I, sir.
Okay, nice.
And in other case, then it will be,
that can be
sir,
H as well,
B,
not I.
then B, and then D, and after that we're going to have this one H, sir.
So can H can be
Because
there if we don't consider
it says because adjacent, no, it it shouldn't be adjacent, sir. So that is the reason.
Shouldn't be connected, right?
Yeah.
Yeah, right.
Sir,
So-
can we mark H instead of I in the same F, A, and H?
Lots of things are possible. Lots of probabilities are there.
So many things are possible, but let's
Okay,
discuss what I have here.
Yes,
okay?
yes, okay.
Yes. So many possibilities are there. So I think even Vishwajit Rai has done with the same procedure, right?
Yes, sir. Yes, sir. I have done this.
Yeah. Okay. So let's just go with this. So if I'm giving a red color to F, so I cannot give it to what? J, B, and G.
B and G.
Right? And likewise, I can give it to A. If I'm giving to A, then I cannot give it to J, right? I cannot give it to C, F, D, right?
E, sir. Not A.
And yeah, E, sorry. So I cannot give it to all of these, right? Then I can give it to I.
Sir,
So if
what
I can-
about
what about what?
what about F? Okay,
Now
we
look
can't
at
give
if I've
F because we have given
because yes, it's just because of that. So now what? Now let's choose. Right. So now let's go with the next color. So
Sir,
it's
instead of A, if I put the red color on D, that time.
that's okay. That's okay.
Okay, na? Okay.
Yeah, that's okay. That's
Sir,
perfect.
why not B, sir? Green.
C, because C I have given. That's why.
Oh, C and B are connected. Yeah.
Yes, yes,
Yes, sir. Yes, sir. Yes, sir.
Okay. So now you can see that. Now if I give it to J, then of course this is perfectly fine because all these three have a different colors. So that's perfectly fine. If I give it C, if I color C, then of course it satisfies the condition with A and I. Then I cannot give it green color to E. I cannot give it to D, and I cannot give it to B, right? So these three are gone. Then I can give it to H, right? I can give it to H, that is perfectly fine, or I can give it to G, right? So I gave it to G here. All right. So if that's the case, then what? Now next is
BDH.
yeah. So BDH, and if I give it to them, then I'll be just left with one, and that has to go with another compartment, that is E. So that means the chemical E has to be put into a different compartment altogether, right? Or you can think of any other. It's just the way we choose the colors, right? So you see this, all these chemicals could be actually put in 4 different compartments, and you read it in the very beginning saying that all these are chemicals. This vertices indicates the chemical, and when they are connected, they are explosive, right? So if you put it in the same compartment, that is J and F, it'll explode. Now you see this. Now if we have just 4 compartments, we can keep all these chemicals together. You can just think of how its applications, right? So it's kind of interesting, right? I hope this is clear to all of you.
Yes.
Yes,
sir.
Yes,
So the answer is 4.
Sir, you need not have to do the call complete like
Exactly.
9. Only if you get 2 lines, I mean 2 vertices, it's enough. You can write it down.
Exactly. That is perfectly fine. And even Kajri was telling that, Kajri Saha, that you know, it is better to choose that vertices which has the highest degree, right? So if you select A, suppose, then what? Now you can see that, of course, you know, like if you choose the highest degree, you can actually think of that, you know, you're actually covering the most of the vertices at one go, and you know, you can actually solve that. So that is perfectly okay. It will not be that way. You can do it in any way. Eventually you will come to the answer if you use this. You just have to obey one thing, that is no 2 edges shares the same color. That's all. Okay, fine. So having known this, now there is some extension let's do over here. Okay, so that is okay, fine, vertex coloring and all that things. Now we are adding some edges without violating any conditions for this coloring. Okay, so could you tell me where all that edges can be? You understood?
Yes,
now what I'm trying to do is I'm trying to add more edges to this particular graph, and I'm making sure there are only these colors.
C2F.
You can
C2F.
C2F, yes, that's allowed.
H2F.
Okay, so first let's do it for this. C to F, yes, that's allowed. Is there any more that we can get it in this pentagon?
Sir, A to F.
E to F. E to F is already there, right?
A to F.
D to E.
Sir, D to E.
Sir,
Yeah.
what is going on?
D to E.
A
Okay,
to
you
F
did not understood. D to E is perfectly fine. Yes.
and A to F.
So
A to F, yeah.
A to F. Yes, A to F is allowed.
Sir, F to H, sir.
H to F.
What to what? Sorry.
F to H, sir. F.
F
The
to
same
H.
thing. A.
H. Yeah, H, F or H, F, H.
Yes, yes. Sorry, I didn't get you. From where to where? F
Sir,
to
F,
H.
F to H or H to F,
to
sir.
C, sir.
F to H. Okay, yeah, that is allowed. Yes, you can have that. Okay,
F
so
to
let's
C.
F to C. F to C is done. Actually, we did that. So let's. These are the internally thing that you can have.
Yes.
Yes, sir. Yes, sir.
Yes, sir.
But you cannot have A to E directly connecting internally because it will lose its planarity, right?
Right.
It won't be planar anymore. But you can connect it this way. Sorry, it's basically the same color. That's why you cannot connect it. I'm sorry.
So D to E is also possible, sir.
Sir, J to P also, sir.
D to what?
D to E.
Okay, sorry. What is possible? Could you come again?
D to E, sir.
D to E is possible. Yes.
No, it will make the.
No, it will cross.
No, it will cross that.
Will not make the graph planar.
From outside.
You can come from outside. That is allowed.
Sir, J to P is not allowed, sir.
See, sorry, if it will come from outside, then H to B also allowed, sir. Then
H to B. Where is it? H to B.
H to B, sir.
Even that.
Oh.
No, but H to B is already connected.
And F to P, sir, from outside. G to P.
F to P. Let's
to
look into
P.
this. Yes,
H
yes.
to
Even
P
that
is
is
not-
allowed.
Is allowed, sir. Both are green color, no, sir. How can?
Those are two different color, yellow and
F.
green. That is
Yeah,
allowed.
F to P.
So likewise, you can think of many other
Sir,
things.
J
You have
to
to
P is
mention
not
that.
allowed, sir.
Which to what?
J to P.
D to P, is it?
No, J to
J
P.
to P.
J to P. J to P won't be allowed because you will have to cross these edges and go, right? So that's why it won't be.
G to P.
So crossing is not allowed, sir.
Crossing is not allowed because you lose the planarity. Okay.
D to B is also allowed.
Okay. So this gave you, and some of you might be wondering what is planarity and all, right? So let's discuss that planarity. That is why this additional thing it came into. Okay. So no worries. But now all I wanted to give you an idea about here is like you can think about, you can have an edges, but you're not violating these conditions. Now, since you are able to answer this, it actually indicates that yes, you know now what is a vertex coloring. Okay, so that was the whole motivation behind it. You won't be definitely asked this kind of question. It's just directly coloring.
Sir, your voice is low again.
Okay, sorry. Now it should be fine. So now what is planar graph? Now I was talking about planarity, right? So what is this planar graph? So a graph is a planar if there is a way to draw the graph so that no edges are intersecting each other except at vertices. Over here, when I was telling you that you can connect actually D to E, right? So you can come across this from outside, but you cannot come from inside because it will be intersecting these other edges, right?
Yes, sir.
That's why it was like that. So, so when you were connecting it from inside, you are actually violating the planarity definition. So you have to come from the outside, right? So that was one thing. So now you understood what planarity is, okay? So what? Let's discuss what are the possible planarity for this particular graph, okay? So now you see this A. Now these are the vertices A, D, F, E, C. Now we have to draw the edges such that it is still a planar. Okay. So internally, what all things you can think of? Can I have an edge between AE?
Yes, sir.
Yes, sir.
Yes, sir.
I can also have between AF.
Yes.
Yes, sir.
And that is happening internally. I'm not looking at external edges, right? I'm not drawing the external edges, but internal edges. I can have an edges between AE and AF. Of course, you could have thought between CD and all that. But when we have an edges like this, AE and AF, I cannot connect this AD together here. If I connect it, it loses its planarity. So what I'll do? I'll take it from the outside. So this is one way connecting it.
Even
now I can also
CF
connect,
also, CF also, sir.
CF I cannot do this. If
No,
I
no,
have
externally,
ED.
sir. Externally, we can do.
No,
Other-
but
internally we can't do, sir.
Right, but you cannot do externally if I have ED.
Yeah.
Right, because then I have to cross this and go there. Right. So then I cannot have that. Right.
Yes.
Right, sir.
So that's one way of thinking. So how many edges do we have altogether? Now you can think of like
4.
4.
Now could you tell me what will be the minimum color for this graph? Just think of it.
5, sir.
5 colors, sir.
3.
5, so it cannot happen.
3, sir.
At max it can happen is 4. With 4 you can actually color all the planar graphs. 5, 6, please do not give answers in your end term exam. You will never have that. Because this is one theorem. If the graph is planar, you can, with the 4 colors, you can actually color a planar graph. At max. Like, yeah, so you cannot go with 5 and 6 if it's a planar graph.
I
Sir,
thought
all
this
are
all
connected
vertices are
with each
connected.
node, so
All vertices are connected, then the color of the graph
yeah.
is N.
Okay, so now let's look at this. If I give red color to A, okay, can I give it to C? Can this be red? No.
No, sir. No, sir.
E, no. F, no. D, no. So then what? I have to give different colors. So then I have to give, let's say, green. If I give it green to this, what then?
Then C may be green hot. We can
E or
paint
C can get.
C or E. Either C or E can get.
So again, what can you think of now again?
All are not connected here.
Which is not
Why that
connected.
outer edge is already there, na? D2C and D2E.
I thought all vertices are connected, like C2, then there's a red line.
D is connected. All vertices are connected only, no? If this is green, then what about this?
This can't be green because C and D are connected.
Yeah, they are also connected, na?
Right.
The C and F are not connected, so they can have the same.
C and F are also connected.
C and
C and F are not connected.
D and F connected.
That's why you will come back to
D
4
and E
colors.
connected.
And you know, we
okay.
misunderstood. Yeah, that's how you will get. So now if this is green, now what about this? If I give it a blue color, now I understood that I got 2 colors, right?
Yes.
And I'm not coloring any other vertices. Now what about F? Now if I give it, let's say red. Okay. So if I give red to this,
then C.
Then
C
these
can
two are
be
already
the same
colored.
one.
Then I can
Colored.
give it, I cannot give it to this, but I can give it to C.
C, yes, sir.
Yes.
Now I
C
have,
and F can be different, can be same color, so
yes,
it will be
now I have
4.
So understand this. Please do not give answers at, you know, some random answers like 5, 6, 7, because all planar graphs can be colored with 4 at max, like 4 colors. It will be lesser than that.
Sir, A to F is connected, no? In this.
So given that number of vertices is 5, right?
No. It not. Let it be 100 also.
Oh, okay.
Yeah. All you have to mention is there is it's obeying the planarity. That's all. If it is planar graph, then yes, like 4 color will suffice the need at max.
Sir, you started with A red, and then F and A are connected, so we cannot.
Now if I started with red, I give red color to A, right? So if I give it red color to A, then I cannot give it to any other vertices.
Yes, sir.
Right?
Oh, right.
Yes.
Similarly, if I give it to D, if I give it, let's say, green color to D, I cannot give green color to any other vertices. Check.
Yes, sir.
Right?
Correct.
Now if I give a blue color to F, can I give it blue color to any other vertices?
No, sir.
You can give it to C. You can give it to C. Look at that. You can actually give it to C.
I don't know that the theorem, the planar theorem.
No problem, but now you should get it now.
Yes.
Okay. Now you see this. Now if I'm giving a blue color to F, then I cannot give it the blue color to C. Sorry, I can give it a blue color to C, right?
Yes.
Because they are not connected.
Yes.
Now how many colors I have used? 3 colors. Now come to F. Now come to E. Now I have to definitely use different color to this, right?
Yes.
So that's going to be the 4th color. Isn't it?
Yes, sir.
Okay. So that's all. That's all about this. This is just out of curiosity I asked this question. But you should understand that, okay?
So is this the reason that when we draw a diagram, triangle,
Right. You can think it in that way.
Yeah, planar, it is called planar triangle, right?
Yes, you can think it in that way. Yes, that is the converse way of thinking. Yes, right. Okay, so now let's go for the next question here. Now it's again like similar to that. An incomplete undirected graph is shown here, and the numbering on each vertex denotes the color of the graph. So now if you can look at this 1 1, so that means they are of same color essentially, and 2 2 represents they are of same color, and 3 3 they are of same color. Find the number of maximum edges that can be added to the given graph such that the coloring is retained and the graph is planar. So what is retained? Coloring is retained and it is a planar graph. And what you have to give me answer? Find the maximum number of edges that is possible. So over here, you don't have any formula as such. All you have to do is just sketch it and see. Okay, and then give me the answer. But all you have to obey is the planarity is obeyed. Okay, so take 2 minutes, maybe take 3 minutes. So I can start at like 9:33, 9:34 maybe.
Sir, I could not understand the question actually.
Okay, so over here you see these numbers, whatever you see these numbers, right? So 1 1, it indicates they are of same color. You can think one as the red
because
color.
they are not connected. Because they are not connected.
You can think it in whatever way, but over here we are given a color. Okay. Now I'm asking you how many edges that you can connect so that the coloring is obeyed. Okay.
Sir, for that,
it is a planar.
I got it.
Sir, for that we will consider the outer loops also, no?
Yes. Outer edges is also allowed.
Okay, sir.
Okay, so take 3 minutes and give me the answer.
Hello, sir, are you there?
Yes.
So it will remain a planar graph, or it will break that property.
No, you have to maintain the planarity.
Okay.
Yeah, and also you have to obey this color property. Okay, so both.
Done, sir.
Nice. So let's wait for another 2 minutes maybe, because only 22 of you have given this response.
Okay, I think I too did that. Let's see this time if I could give correct answers.
Okay.
Yes, sir. Done.
Nice. So is there anybody who is still solving this?
Done, sir. Done, sir.
All of you done? Do any of you need one more minute?
Done, sir.
Okay. Okay, fine. Since nobody is responding, let's see what are the popular responses. So 4, 6, 5. So I asked what? How many edges that we can add? Maximum number
Maximum
of
edges, sir.
So it's not coloring, so do not give answer as 4. I don't know why, but I got that feeling that, just because I told last time that, the coloring thing. So this 4, but let's see. 5, 6, 8, 9, 5, 7, 7, 4, 8, 9, 7.
7 is the right answer.
Yeah, 7.
So 6, I believe 6 is the right.
5, can
7. I think 7 is possible.
Okay, fine. So let's discuss this. Maybe it will be hard for you to tell it just here. So what I'll do is I'll just give you the explanation for this, okay? Because even if you're telling which is connected, what will create simple confusion to all of us. So let me discuss this. So what are the two things that I have to over here? That when I'm drawing the edges, I'm not violating the coloring concept, right? And secondly, I'm free to draw a number of edges, but all I have to do is what? I have to make sure that the graph is planar, right? So these are the two conditions that I have to think in my mind, okay? So having known that, look at these two things. Now this is the graph, right? So what are the inner edges that I can do? Now you see this is 1, so I cannot connect this. 1 cannot be connected, right? But 2, 3 can be connected. So what I have drawn? The inner edges. So you can see that the inner edges are connected first. So 2, 3 is free to connect.
Yes, sir.
1, 3 is free to connect. Can you think of anything over here which is free to be?
Sir, 1 to 2, sir. Sir, 1 to 2.
1 to 2 is already connected.
No, from outer side. 1 to 2.
But it is
sir.
already connected.
No, not this one, sir. The 3 point, that one from
okay,
2,
this
sir.
one.
No, this one, sir.
The below one, sir.
Below
yeah,
one.
This 2, above 1 and below 2, sir.
Okay,
These
so that's
two and
externally.
above one,
That's
yeah.
externally. That is
Yes,
in. So we are talking about the
First
inner
we
edges.
will go with inner.
First look at the inner edges and then we'll look at the outer edges.
So
okay?
inner, it's not possible now.
Inner it's not possible because you have to cross this edge and then go, right? So then you will have to think of outer. So first let's look at the inner edges. So in this pentagon, as you can see, these are the only two inner edges that is possible. Over here, likewise, I can think of course, I could have connected this 1, 3 here, but it's okay that I did not connect this. If I was connecting this, then I could have thought of, if I would have thought of connecting 2, 3 back then it would have been crossing there. So I could not have connected this, right? So the other way of thinking is 2 and 3 can be connected and 1 and 2 can be connected, right?
Yes, sir.
These are the two things that I can think of. I mean, this is the maximum that I can think of, right? So now you can see that these are like, there are 4 inner edges. Now what about outer edges? As Vishwajit Roy was telling, so you can actually connect this 1 and 2, right? So this has been connected here. Like, look at this outer edges. Likewise, I can connect this 1 and 3, right?
Yes, sir.
I can do this as well. Now what more I can do with this? I could have, of course, joined 1 with this 3 also, but let's see if there are any other possibilities and which can give me the maximum one. Okay, if I would have connected this, then definitely this would be creating a problem for me. So first I'll connect with 2. So now
I missed it.
So if I connect this 2, 3, I can connect this 2, 3. I can connect this 2, 1, right?
2, 1.
And I can even connect this 2, 3.
I missed that one, sir. 2 to 3, sir.
Yeah. Okay. So now how many edges that we can have maximum?
9.
Altogether 9 is possible, right? The answer is 9. So these kind of questions, this is for practice, right? So when you're practicing, when you're keeping those concepts in your mind, you're actually, you are kind of understanding that concept, and also what like you can actually memorize that concept, like what that is, right? So these are the things that you can do, right? So over here that we had to obey 2 things. That is, our questions can be asked similar to this, right? Wherein, the planarity and the coloring is being obeyed. So I'm saying that, this is the way we can actually create the questions, right? So this is one thing that you can actually think of. Now let's discuss something about DAG. So I felt like, asking questions.
Sir, one doubt there. So if we are not following the same approach, let's say someone is taking some other step, and I mean to say different sequence, then they will still achieve the same answer, or they will get a different answer.
Again, but if you're taking a different thing, all you have to do is you have to maximize it. So let's say if in this previous one, previous one over here, when you were trying to draw that, let's say the external edges or the outer edges, the other way of thinking was you could have connected this 1, 3, right? And you could have actually connected again this 1, 3, but how many edges you were getting altogether? No, but this 1, 3 was connected. I'm sorry. You could have actually connected just 1 and 3. That's all, right? So when you had this in between, you were actually crossing all these, right? So you could have though created one possibility here by connecting 1, 3, but in the process you are neglecting these 3 edges, which is something you have to maximize, right? So you have to actually think over there that if I'm taking an edge from here, am I losing any other edges if I had to connect from here, right? I hope you get it.
So even if we connect one, we'll get the same number of edges, sir.
If you connect 1 with the 3 from 1, is it? Okay,
yes.
so you
2,
connect
3
1
will,
with the 3.
Yeah, 2, 3 will still remain there.
2, 3 will still remain there. Okay, fine.
Yes. And 1, 3 will get connected. And also 1, 3, the below one will also get connected.
So let's say when you're connecting 1, 3. Okay, 1, 3. Yeah, still you can get the same. Yeah, I'm sorry. You can still get the same.
Sir, the question is like the possibilities are many. So is there any kind of steps or procedure you should follow so that there won't be mistake?
This is something like you just have to practice and learn. That is the only thing.
Okay,
You don't
okay.
have like, yeah, you don't have anything like that. Okay. So yes, this is about this. So next is about DAG. Okay. So DAG, as you can see, it is not asked in your graded assignment. But if you want me to discuss more about DAG and its application, I can do that. Is fine. But this can also be discussed in the next session. So what do you want me to do? Do you want me to discuss DAG here?
Yes, sir.
Yes, sir.
Okay. So maybe I'll not use slides here then. And I think if you have gone through, or maybe I can just write and show something like on DAG, and then we can just try to quickly finish it here, because DAG needs bit understanding. So let me just think first. Let me just check your knowledge, like how many of you know what DAG is, right? So I can just take this and just discuss with you DAG, and there are 2 applications on DAG, and that's the maximum questions which we can ask, right? So what is DAG? So I'm done with this periodic slide.
Acyclic graph.
Okay, just a minute. So basically I'm done with this slide. So this is about DAG, some facts about the DAG, and one question on DAG has been asked, which I believe I can cover here when I'm discussing there on this one note. Okay, so it's about topological sequence that I can see. So I can just leave this part now here. It's just the same thing, topological sequence, which I can actually discuss, here with one particular question. So that's fine. So we can just end this here, this slide thing. All right. Okay. So this is about this. So let me just open this and just quickly discuss what DAG is, and then I would see, like, what more we can do about this. And I think we had one question on activity, which I'll take that. So now look at this. What is directed acyclic graph? So just a minute. So DAG full form, we all know what it is.
Directed acyclic graph.
So let's bifurcate the meaning. Directed acyclic, and it's a graph. So first of all, what it is a directed, right?
Yes,
so the graph is directed, and it is acyclic.
One direction. That is going in one direction.
There will be no cycle in that graph.
And there is no cycle in the graph, and it's basically a graph, right? So maybe I'll just check your knowledge. So if I have a graph like this, let's say A, then I have this B, let's say I have C, and then D, right? And these are connected. Let's say A is connected to D, okay? C is connected to D, let's say like this. A is connected to C. This is connected to this, okay? And then let's say this is connected
B to C, sir.
This is one. Maybe I can just give you another arrow here like this. Okay. Now I have, let's say, another graph. You can solve this, whether this is DAG or not. I'll give you 3 options, and I want you to solve that in video. Now this is B. This is C. And then I have D here. Let's say this is connected like this. Okay. Let's say I have another graph, and this is something like this. Which among them is DAG?
Which is DAG?
Two is DAG, sir.
Is that?
No,
One is not.
Sir,
One is not
sir,
there.
one is not DAG,
Other
sir,
is a
because
DAG.
BC, sir, BC, if you see the arrow, sir, it is not double direction, sir.
So this is not DAG, is it?
Yes, sir, it is not DAG.
Right.
Who is
What
DAG,
about
sir?
this? This
Who is DAG,
DAG?
sir? Yes,
What
sir.
about this?
It is not DAG, sir.
2 is not DAG.
2 is not DAG.
2 is
Even
not
2
DAG.
So basically none of them is DAG.
Yeah.
Why
Yes,
2 is
none
not
of them
DAG?
is bad.
Because there is a
Cycle.
cycle.
If you see a cycle B, C, D.
It forms a cycle.
Yes, here it forms a cycle. That's why it is not a DAG. Right. So now this is just to tell you what is DAG. So now again, when
Sir, I
didn't
have a small query. In this third option, because the age is bidirectional, that's why we consider it forms a cycle, right?
Correct.
Am I right?
Yes, yes,
Okay.
yes.
Correct.
So essentially you can actually say that this is like this. Okay.
Okay. Yes. Okay. Thank you.
Yeah. So now you can understand this. This is not a DAG. So when it is DAG, now look at this. If this was not there, if it is just this, is this a DAG then?
Yeah,
Yes,
this is a
sir.
DAG.
Yes.
Yes, sir.
Okay. So is this a directed graph? Yes, this is a directed graph. Is this a acyclic graph? Is there any cycle in this?
No, sir.
No. So if it is directed and it is an acyclic, then it is a DAG. Then it will become a DAG at that point. Okay. So clear? Now you understood what is DAG, right?
Sir, in the first graph, now you are saying because the direction is not uniform, that's why it is breaking the rule. Like A
It
to
was
B.
bidirectional.
Yeah, okay.
It's basically this has been inserted. This third condition is put in here.
So if we start from A, we can go B, C, and D, but D to A is not possible. That's why
Actually, this thing what I drew, right? This was forming a cycle in itself. This itself was a cycle. You understood?
Okay.
Because of that particular reason, this is not a DAG.
It means actually, sir, each edge directed from one vertex to another in a such a way that those directions will never form closed loop, sir.
That is another way of saying it.
And one more thing, sir, there must be one vertex which didn't have any incoming edges. It must
Those are properties. Those are properties. That is, and over here, yes, that you can actually say this, because over here you are actually right in that aspect. So let's see. That is some of the
currently,
properties.
currently A1 is cyclic or not cyclic?
Currently A is DAG. It is acyclic. Second is not, and third is not. Currently, as per this given condition, because there is no cycle here. Can you see anywhere there is a cycle in this graph?
It is connected, but from D to A, it is the direction is opposite. Actually, I'm not getting it. Actually,
it's not a cycle.
Okay.
It would be cycle only when this was happening. Now look at this. It's forming a cycle. You can actually go to A to B, B to C, and C to A. Right?
Okay.
Now look at this. You can go to A to B, B to C, but you cannot go C to A. So this is not a cycle. Basically, in a cycle, you can actually cover all the vertices. You can go from each vertex to other vertex. So over here, when you're talking about DAG, even the subgraph should not be an acyclic graph, because if a subgraph is if the subgraph is cyclic, it means the graph itself is cyclic, right? I hope you understood.
Yes, sir.
Oh, okay.
Okay. So now this is about DAG. You understood what is DAG now. Okay. So then what do we do with DAG? There are two applications. There are other applications too, but majorly we discussed two applications. And what are those two applications? So one is topological sequencing. Okay. One is topological sequence, and the other thing is
longest path.
Longest path.
Longest path.
Longest path.
Longest path. So you just have to focus on this thing. First of all, you should understand what is DAG, and these two done. That's all. This topic is over. Okay. So now let's discuss this. So before going at these 2 points, let's first discuss what are some of the properties, right? Now, this was my DAG, right? Could you tell me something about the in degree for this? Now you understand what is in degree and out degree. What is in degree?
Incident,
incoming edges. This is the coming in.
Incoming edges and outgoing edges.
Out degree.
Directed away from the vertex.
So what I'll do is I'll write in degree here and out degree this side. Okay. So what is in degree for A?
0.
0.
What is out degree for A?
3.
3.
What is in degree for A? B? 1.
1.
What is
1.
out
1.
degree for B?
1.
1.
1.
What about C? What is in degree for
1 1.
1. 1.
2 and 2.
2.
2 and
What
1.
is
2
out
and
degree?
1. 2 and 1.
1.
1.
What about this?
2 and 0.
2 and
2
1.
and 0.
For D, it
0.
is 2 and 0.
And 0.
0.
So what? So I'll just write down this is in degree, and this is out degree. Okay. Now let's discuss some of the properties, and it's okay if you can write these properties. It will be good for you. If not, it's fine. So some properties which is actually which will be helpful when you are solving some particular questions. Okay. So what are these properties? Okay, so first property that we can think of is there must be there must be at least one vertex with in degree what? 0.
0.
Right? So that is 1 point. So at least one vertex with degree what?
0.
Sorry, in degree 0. Not
In
degree, but in degree 0. Okay, what more can you talk about? Can you think of any other properties?
At least one vertex without degree 0.
No. There must be there cannot be a cycle in the day.
Okay, so of course that's first of all it has to be DAG, then you will look out its property. So that is, you cannot take that as a property. What more then? Can I also say that there must be something where out degree is also 0?
Yes.
Yeah.
Yes, out degree has to be 0. At least one vertex.
So at least that I can think. Also, I can say that there exists a vertex with what? Out degree 0, right? Also, there exists a vertex with out degree 0. Without degree 0. So you can see here itself, right? This was out degree, no?
Yes.
So this is my second property. What about third property? Now what if I remove this? Let's say if I was removing this vertex A, now if I remove this, whatever I get back, that is again a DAG.
Yes.
So if I remove a vertex within degree 0, the resulting graph is again a DAG.
Yes.
That is again a property, right?
Yes.
Right? So if you remove a vertex, so pardon my bad handwriting, you can just, whatever I'm saying, you can just write it down. If you remove a vertex with in degree 0, the resulting graph is DAG again, right? This is what we can say. Is there any other thing? We can just think of these three properties, right? As if now, if you have any more properties, you can actually jot it down or put it in the forum. But what I can think of right now is just these three properties. Now, based on these three properties, let's discuss what is topological sequence. Okay.
In that, if we join another two vertex, the graph will be cyclic.
Another two vertices, if you join, is
extra? The DAG is minimum a cyclic graph. If we join extra two vertices with not join in DAG, then it will be cyclic.
Okay.
This is for tree, not for.
Okay. Maybe I will not write it down here, but fine. If I don't know in what context you are saying that, I will actually have to look into that part. Right now, I'll have to look into that part. So let me not just get into that aspects right now. Okay. So let me just discuss this now. What we discussed, what is DAG, and we also discussed three properties of the DAG, right? Now let's discuss what is this.
No, sir, I mixed up with tree.
Yeah, that's what even I was thinking, because
I mixed up with tree, sir. Sorry.
if you were to ask me, I could actually tell you where you are going wrong, because if you, let's say if you have BFS tree or like DFS tree, if you have back edges, right?
Yes.
Right. So if you have a back edges, that it will form a tree.
Yes.
It will form a cycle.
I'm talking about tree. If tree where that minimal line, if we draw one more line, it will be cycle. This I spoke down. Yeah. Sorry.
Okay, no problem. No problem. So now let's discuss what is topological. Do you have any doubt till here? No doubt, right? You're convinced with these three properties, what has been written here?
Yes, sir.
Right?
Yes. What is the third property, sir?
Third property is, if you remove the vertex with in degree 0, the resulting is again a DAG. The resulting graph is again a DAG. Now, for example, if I just remove A from this, now the result, what I get from here is again a DAG. So what I'll be left with at that point of time?
B, C, D.
B,
C,
C, D. What is in degree of B? 0.
0.
Out degree 1.
1.
1
and 1.
1
and 0.
And 0. Now look at this thing. Is this a DAG?
Yes.
Yes, sir.
Topological sorting.
Yes.
It is a DAG, right? Why? Because you see, you have, because of again these properties, you see this, because first property actually holds good, because you have at least one vertex with degree 0, and you have a there also exists and what
Fulfilling the first property.
0, first two properties, and third property is just that, that when you still, again when you remove this B, you will still be DAG, right? So that's how you can see it. All right, so I hope you understood this. Now let me quickly discuss the next two things, that is topological sequencing and longest path. And we'll see if we can discuss more questions on this, like maybe in the next classes, because this has been asked in your graded assignment for week 11. So I think this topic will be again discussed. But just to quickly give you an understanding what it is, so that you can actually solve those activity questions what is provided. So now what is topological sequencing? Okay, so let's look at that part. Okay, so
this means cannot have like any cycles, sir.
That's right. You cannot have any cycles for DAG basically.
Because the edge, because the edge into the earliest vertex of a cycle would have to be like oriented the wrong ways.
Right. That is perfectly right. Now look at this part. Now let me say I have this graph view, and now I'm going to do topological sequencing. Let's say this is connected like this. So now if you had to check in the first three examples which I gave you, and if you had to check whether this is DAG or not, how will you check this? Now look at this. It has got in degree 0, right? This one, you are checking whether this is DAG or not. So what is in degree for this? 0. Now look for any graph without degree 0. Any vertices without degree 0. Is there any vertices without degree 0?
No, sir.
No. So then there it's gone. You cannot think of this. What about this? Is there any in degree with 0 in this?
Sir, are you sharing the screen?
No.
No, sir. It's not 0, sir.
No.
It's 1.
And also the out degree is
1, sir.
So again, this is violating both the conditions, right?
True,
so like that you can think of, right? Fine. So let's do a topological sequencing. So what do you do in topological sequencing, right? So what you do here is, I'll just tell you what is the procedure behind this. First, what you do is, step number 1 you can think of is find the in degree of all the vertices in the DAG. Okay. So what is in degree of? So first I'll write down in degree of all the vertices of this particular DAG. First, are we convinced is this a DAG?
Yes, sir.
Yes, this is DAG. So now I'll just write down in degree for all the vertices. What is in degree of A?
0.
In degree of B?
1.
1. B.
In degree of C?
2.
1, sir. 2.
2,
in degree of D?
2.
Sir, 2, sir.
Now, okay. So that is the first step. Then what? Once I write the in degree for this, then what do I do next?
Out degree.
No, I'll not do that out degree here.
Okay.
So what I do here is, in topological sequence, it's basically you write down sequence here. And how do you do this topological sequencing is basically whichever vertices has got in degree 0, that comes in your topological sequence set. Okay, so now over here, which vertices has got in degree 0?
A.
Yes, sir.
So that comes in my topological sequence. So that is my first element in this topological sequence set, A. So this is A. Now if I do this, that means what? I'm removing this now. Now what I'll do?
Then we
Now
have to
I'll check
remove
for the
A.
next one. So now what? Now if I remove A, then I'll also have to remove all these.
Yes.
All these
Then the
in this.
in degree of B will be 0.
And now what I'll do is I'll just write down. I will write down the remaining vertices, and then what do I write? I write out the in degree
B
for
in
each.
degree 0, C1, D1.
1, 1. Now what from this? What is the next one will come into this topological sequence?
So B, sir.
B.
B removed.
So now what? Now B is removed.
Now the
removed
in
to edges.
degree of C and D 0.
Right.
Now
what
So,
you go
sir,
with?
the
So we
node
can
with
C or
zero
D.
in degree, we
C0,
will remove
D1.
it, right?
Okay, just a minute. You have one question. Yes, what is that question?
Yes, sir, just a small query. Like when we find a vertex with 0 in degree, we will simply remove from the graph, and the remaining elements combining together, we will put as a newer graph. Is it?
Correct.
Okay.
Okay. Now look
And
over
the
here.
removed thing will be put in this TS set, right?
Right. TS is nothing but topological sequence. It's just the short.
Okay. Okay.
Right. So TS is this. Now what? Now C comes in the next entry. What about then?
Now
The last will be D.
0, D1.
So this is all right. So this is what the sequence is. So this is something, it's basically, where can you think its applications? So you can think of these applications now. Let's say if I have set of work and I say that, and I have mentioned that, this is how my works are interconnected. Then what is the sequence that I have to follow in order to finish that work? So if you have to prioritize your work, then which should be your first priority of completing your work? That you have to complete the work A, because you see your work C is dependent in A. If you cannot complete A, then you cannot complete C. So essentially you'll have to complete A first, right? So this sequence tells you that which work has to be completed first in order to complete the other. Essentially, if I have to look into work related time, so over here, I can say that work B is dependent on work A. That means if I have to learn, let's say this is maths 2 and this is maths 1. So essentially it says what? If you have to learn maths 2, then you must learn maths 1 first, right? Your maths 2 is being dependent on maths 1. So that's how you're building the sequence. Likewise, if I have to say this one, then I have to say, let's say this is, if I have to say this is, let's say stats 2 and this is maths 2. So if I have to do, let's say, machine learning, then basically machine learning I can learn only when I know maths 2 and stats 2. Right?
Yes.
So
Yes,
what it says about what? So it talks about which work has to be completed first. You understand?
Correct, sir.
Yes, sir.
Now some of you might be thinking, what if we had some more vertices, or like some more vertices with, let's say if I had something like this, maybe if I have to draw, what if you had the condition like this? Now if you had this E as well, okay, and this E was connected like this, okay, so this E was connected like this. Now if I'm removing A from this, okay, now if I'm removing A from this, what I'll be left with? I'll be left with this B, C, D, and E. What is in degree of B? 0.
0.
Degree of C? 1.
1.
Okay,
1.
This is what?
2.
Is this a DAG first of all?
Yeah.
Yes, sir.
Yes.
Yes, it is DAG. It is
It is DAG, yes. So this is 1. What about this? 2.
2, sir.
Over this is 0. So now what should be the next sequence here? Should I take B or E?
Anything, sir.
You can take anything at that point of time, right? So when you land up in situations like this, you can take anything. Okay. I hope this is okay.
Okay.
Yes.
So given graph, many topological sequences possible.
Like you can say two are possible.
Okay, sir.
When you remove E, then you will be left with, then the next task you will have to do B, and then C and D. And if you go with B, then definitely you will go with C, and then you will go with E and then D. So that will be like two sequences at that point, right? I hope this is okay.
Sir, in many graph, the inner sequence can also be changed. Like if we can.
Possible.
Okay.
Yeah, it's possible. So this is about topological sequencing. Okay. Now I'll quickly tell you what about. Okay. So now let me just ask you a quick question on this. Let me check your knowledge, like how much you're aware of this. Now look at this. Now this is another graph. Okay. 1, 2. Let me say this is not 1, 2. Let me give it as A. This is B. This is C. This is D. And let's say this is E. Okay. So now is this a graph?
Yes.
It is a graph.
Yes, sir.
All of you agree?
Yes, sir. Yes, sir. Vertices are not connected.
Is this a acyclic graph?
No, sir.
No, sir.
Why? Is this a cyclic graph?
No, sir.
No, sir.
No,
It's
sir.
not cyclic graph.
It's
Trivial or
It's
something
acyclic
that
graph.
is-
Yes, sir.
Right? So first of all, is this a graph? The answer is yes.
Yes.
Is this a acyclic graph?
Yes.
Yes. Is this a DAG?
No, sir.
No,
No.
there is no
Right.
direction, no
Yes, sir.
edges.
Right. Because you don't have any directions. You cannot say whether it is directed or undirected, right? So I
Yes.
cannot say anything. Maybe you can say unconcluded or unconclusive, maybe. So you cannot say anything about that. You cannot say,
Yes, sir.
some of you can say, yeah, this is DAG, and some of you can say, no, it is not DAG. So it is unconclusive. You cannot conclude anything here, right? So this is just simply, a concept checking things. Okay. So I hope this is okay. Now let's go with the next part. What is next? Now we understood, topological sequence.
Graph.
Sir, just to
Okay, just tell me a graph with one vertices. How does it look like?
Just a single vertex.
That's all. That's all. So if that is a graph, then all these things can also be a graph, but these are not connected graphs.
Yeah. Some name was there for single vertex mono. I forgot that.
Okay. Fine. So let's go with the next thing.
May I ask you a couple of things here?
Yeah.
Just to like the example what you gave. So this acyclic graph, we can say that we can resemble this with like if we have real-time task wherein we have interdependency,
right?
Then we can try to think that as a acyclic graph and try to come up with a solution of that, how we approach to the sequence of tasks.
Right. Perfectly right.
Okay, fine.
Yes.
We can apply this any work which
Anywhere,
has
but
sequence.
that is just to give you an idea. If you are very strong at one where, right, you can definitely think that at the other where, right? So you can just keep that as a strong point. Yes, this is like, I can use it as work related problems or like anywhere else. Okay, fine. So I'll just quickly discuss this. What is,
Sir,
topology?
I want to ask one question. This is parallel edges or bidirectional graph, both are same.
Parallel edges
and bidirectional graph.
Like, is there a direction in them?
Yes.
To say like this?
Yes. Suppose A to B one line and B to A one line, and then suppose one thing is C to D a bidirectional one line, B two arrow, both are same.
This essentially you can actually represent by a single line, saying that
both are same, right?
You can say. Okay, now let's quickly go to this. Yes, you're welcome. So now let's go to this topological sequence is done. So now what? It's like longest path in DAG, right? I wish I had more time to discuss this in more elaborate way, but let's quickly give you an idea what this is. Longest path in DAG. Okay. So now what, like, I'll just quickly take up one example and just tell you how it is done, how you should actually do it in your exam. But I would advise you to see Professor Madhavan's video and you see that how is he doing in more algorithmic way. But what I'm trying to tell you right now is how you do it in your exams. Okay. So I'm not going very algorithmic way, but yes, like it's just that how you do it in your exam. And this is something you do it after a practice. So I'll just discuss that with you. Okay. So now let's say I have this graph. Okay. Tell me, is this a DAG?
Yes, sir.
Yes, it is.
Yes, sir.
Yes, sir. That. Yes.
Okay. So now what I'm doing, longest path, right? So longest path to. So I'm just using a keyword. So it's like longest path to. Let's say this is the thing, and I'm using this word. Let's say LPT. Okay. So what is step one? What do you do basically here is you first in step one.
One thing would be D here. You written
Yes, sir.
B
It is D, or you purposely
Oh.
mention it B, sir, twice.
Okay, so here let me give it as D. It's not B. Okay, so A, B, C, D. It's gone like this. Okay, so now let's see. Here, let's first give it as a step one, wherein you initialize entire vertices with longest path to 0. Okay, so what do you do? Longest path to. Now LPT, you understand, right? What is this LPT? LPT
Longest
to
path.
I is nothing but this vertices. Any of these vertices is 0, where I is belonging to what? Any of this set. So A, B, C, D, or E. So basically what step one says, what? You initialize the longest path to each of these vertices as 0. You understood? So what is this is my step one. So step one, what am I doing? What is the longest path to reach A? 0. What is longest path to reach B? Sorry, B? 0. No. It's just that I'm initializing. So 0,
No, so you
0,
said 0.
0. So you initialize every vertices with its longest path to 0. Okay. In step 2, now look at
So
my
can
step
you
2.
please repeat? I could not.
So if I have to tell you in a very layman language, what I'm doing is I'm saying that the longest path to reach vertex A is 0. Longest path to reach vertex D is 0. So in the first step, I'm not telling you from where to start, but I'm telling you, you are free to start from anywhere. So if I have to reach D, why not directly go to D rather than going from A, right?
Yes.
You understand?
Yes.
It's simple, right?
Okay.
Right. So now I'll just, okay. So is this a DAG? All of you, can you tell me this? Is this a DAG first of all?
Yes, sir.
Yes, sir. It's a
Yes,
DAG.
I
So
can
first
hear.
of all, whenever you get a thing like this, first check it out whether you have in degree 0 and out degree 0. So is there a in degree, is there any vertices within degree 0?
Yes, sir. For
Yes, sir.
Vertex zero.
A.
A.
Okay. And is there any other without degree 0? Yes, I have E. So I'll not
E.
mention that. It's just that for my practice that, I have something like that. Now what? Now if I have to find out the longest path, right? So if I have to find out the longest path to B, then what is the thing I have to do? Longest path to B. So what I'm saying, if I have to reach the longest path to B, but from where do you start this? You start with
A.
You start with A, because wherever the in degree is 0, you start with that. So from here I can go to B or I can go to D, right? So let's say I want to find out the longest path for B first. I could have also asked for D, but I'm just choosing what? B. I'm just going in an alphabetical order. Okay. So what is the longest path to reach B? So what do you do is it's just that, out of practice that you can do. This is what you do is, I'll just write down this small math, you can say. Maximum of LPT to A, sorry, not A, but rather
The previous one.
the previous one, B plus 1 plus longest path to A. So why did I choose A and why not others? It's just because A is within degree 0. That's why I choose that. Okay. So now this will become more clearer when I'm discussing the question, when I'm discussing this. So what I'm doing here is I'm choosing the maximum. Just a minute. I'll just adjust my screen here. Okay. So now it is clear. Now longest path to B is what? It is maximum of longest path to B. Like what is the longest path to reach B currently after step 1? It is 0, right?
0.
So it is 0. So this is not plus, but rather comma. Okay. So either this or this. This is what it means, right? Comma.
Sorry to interrupt. This one, why in step 2 arbitrarily you took longest path of B? I mean,
you could have chosen D also.
Okay, anything. Okay.
But you could not have chosen C. It's just because you have to choose those vertices which are in direct touch with the other vertex which has got an in degree 0. That is why you can choose B or D, any of these. I'm choosing B. Okay, I just chose the alphabetical order. Okay, so over here.
So, sir, one question. So here, in this case, we cannot calculate longest path of E or C, because They are not connected with A.
A,
Right.
yeah, exactly. Just that.
Okay.
Okay. So now look at this. Longest path to B is equal to maximum of longest path to B, comma 1 plus longest path to A. Why A in specific? Because this has got in degree
0.
That's it. So now this is 1 plus what is the longest path to A?
0.
0.
So now which is maximum among this?
1.
So 1.
Longest path to reach B is what? 1. So now with this, I will update this. So what am I doing is whenever I go to step 2, what I do is I just remove this A now, and now I'll be left with just B, E, C. I'll keep the rest with 0, okay? And this D, I did not do anything yet. So I'll just keep this D. Now what is the longest path to reach B? 1. So that is something I have updated. Likewise, now step 2 will be repeated for other things. Now this was initially connected. Now what I have seen is this is what. Now I have just removed this edge from here, right? So now I updated this part. Now what I have to do something with this, right? So now likewise, could you tell me what is longest path to reach D? Again, same way, maximum of LPT to D, right? This time it is going to be D, comma 1 plus
1
longest
plus
path to reach A. Now could you tell me what is longest path to reach D?
0.
0.
1, sir.
0, 0. How it is
0.
1?
So D, A to D.
Initially.
Initially 0. Okay.
So now
But
what?
max
Now,
is 1. That's what I'm saying.
so 1 plus longest path to reach A was what? 0. So what
0.
is max?
1.
Max is going to be
1.
1.
So now what? I'll remove this completely and this will remove 1. So now I'm done with this part. Now which are those vertices within degree 0?
D and
D and B. So I can take any of these, right? So I can do.
In degree 0. Okay. D and B.
So now I'm done with this. I'm just using this arrow to showcase this. So now what? I can either use this B or D, right? So let's say I'm using B. Okay. So now what? When I'm using this, so now you'll see the formula being changed. Now longest path to reach E, I will check, right? So what? Now I'm omitting this thing, right? I'm cutting down this, right? Now longest path to reach E is what?
Longest path to
Maximum
reach
of
B.
1 plus 1.
Longest
2.
path to reach D, to reach what? E, right?
E, sir.
Comma 1 plus longest path to reach
LPT
Sir,
B.
B, sir. Yes.
So now what? Now I'll go again with the maximum thing.
1, sir.
What is LPTE?
0 and 2.
0 and 1 plus 1.
1 plus 1.
So this is going to
So
be
max is 2.
2, sir.
So now what? I'll just write it down in the next step maybe. So it's going to be D, C, E, and I'll just directly write down what is its now maximum longest path to reach E? 2.
So 2.
And what about this was 0, right? Unchanged. This is 0. And what about this? This was upgraded to 1, right? You
1.
remember? Okay.
Yeah.
Likewise, now I will do for what? Now I'll do for D. LPT of D. Sorry, not D, but what? C. Because now this has got in degree 0. So I'll not be doing for this, right?
Yes.
So I'll be checking for C, right? So now what? Now if I do what? Now maximum of LPT of what? C. Because this
C.
comes as it is,
C.
comma.
And
1 plus
And 1 plus
LPT
LPT of D.
D. So now what? Could you tell me what something more about
LPT of
this?
C is
0,
0.
comma 1 plus 1 is equal to 2.
Sir, one doubt there.
Okay.
Once you have done longest LPT of B and LPT of D, you will be remaining with C and E, right?
We'll come to that. Wait. Let's go in the order.
Okay.
Okay. So now this LPT of C is what? 0. Now 1 plus LPT of D is what? 1. So this gives me what?
2, sir.
2 again. So now what? I can modify this likewise. So this is going to give me what? Now C is what?
2.
Longest
2,
path
sir.
to reach C is what?
2.
2.
And what about E?
2.
E is also 2.
Now what? Now what is in degree of which has got in degree 0?
C, sir.
No.
Sir,
C. So now that
C
is something I'll be using. So now, but from C I can go to E. So
Yes.
longest path to reach E will be maximum of
2
what should I
plus
write
2,
here?
4.
Wait. What should I write here? Longest path to reach what?
C.
E. E, not
E, sir. E.
E.
Sorry.
LPT E. 1 plus
1 plus
LPT
LPT of D.
C.
E.
What is
LPT
it?
C.
C.
C. So now what? Could you tell me more about this?
3. 1
Sir,
plus
two.
2, 3.
What is this? Just don't
Two,
go to the
sir.
answer. Go step by step. So LPT of E is what?
2,
2, comma
Plus
comma
1
1
plus
plus
1 plus
2
2, sir.
So what is
is
this?
equal to
This is going to
3.
give me
C.
3. So now this will
Yes.
come down, and what do I get? Yes.
So, sir, it means that that longest path get more modified when we go with the problem,
Yes,
right?
yes.
Because initially longest path for E was 2. Now it is 3. Means it
Now
get modified.
this path you have to choose, right?
Okay.
Understood.
Yes,
So now
sir.
you are getting some understanding over here.
No, sir, I have doubt.
Yes, tell me.
So in the LPT, I understand that step 2, like initially that node A was of in degree 0. So you first derived that LPT of B and D. That is clear. 1 is right.
Okay.
Then after that, what you did actually when
So
you
now
are
what
doing
am I doing here is, now you see, look at this step 2. In step 2, I chose this 1 plus LPT of A. This A, whatever I chose, I made sure that it has in degree 0. Right?
Okay.
So when I do this, when I remove A, I get 2 vertices with in degree 0. Right? I get B or D with in degree 0. I can choose any of them, right? So what did I do?
Alphabetical order.
So I just went in the alphabetical order. I was like, okay, fine. I will find, basically, yeah. So now this B was with in degree 0. So I will not be finding the longest path to reach B, but I would be actually going with E. So longest path to reach, this thing you're asking, right? So I'm sorry, over here, this LPT, why? Because you see here, why did I go with this is just because of alphabetical order. And see here, the in degree for this was 0. So I could have gone with B or D, right? So I chose B. So when I chose B, then I have to make sure that this is A because this was in degree 0, right? And over here also I chose A. It's just because this was connected with this within degree 0. So now when A is removed, I'm cutting down this part, right? So I'll be left with what? I'll be just left with B and D. Now I'm free. Now which one should I go with? I can go with C or I can go with E. If I'm going with E, then definitely if I have to reach E, then I have to make sure that this part will change to B, right?
Yeah, okay.
Because so this was in degree 0.
So once you have taken the LPT of B, you're actually removing only the node A and you are remaining with B, E, C, D. Yeah, okay.
Okay. Now one interesting thing I want you to note here.
Sir, one question, sir. Sir, in degree of B is how comes a 0, sir? In that graph, in that graph, sir, the top graph, sir.
When you this one only, no?
Yeah.
So when you over here it is not 0. This is weight. This 0, what you see is like initial. It's not a weight. Sorry, it's like the longest path, the initialization step. That is why I gave 0.
Oh, okay.
Remember?
Okay. I thought. Oh, I thought you.
No problem. So now one interesting thing that you should understand from here. Okay. Now what is topological sequence for this? Just tell me now. You can just directly tell me. I think you can tell me.
Sir, B, D.
Topological sequence. First, I have to complete task A.
Yes, sir. A, B.
If I do this, I can go with B.
B.
Okay.
D, sir.
D.
Then D.
D, sir. D.
Okay, D.
E, sir. D.
D.
Yeah,
D,
D,
A,
sir.
B, D.
Then it can be anything.
Then
C,
can be anything, sir. C or E. Yes.
Or I can also have the other. Let's look at the other part. A. I can do D. Can I do this?
Yes,
Sir.
Yes,
We
sir.
can do this also.
I can also do C, or I can even choose B, right? So I'll come with that next thing. Maybe I can just write down A, D, B,
B,
and then what? C,
and
C, then last
look at
E.
this. What about this? A, D, C,
B and E, sir.
B and E.
B and E. Yes. So now I want you to notice, just notice this part, okay? Forget about this. This is just like we can have n number of sequence. You know, you can think of, I can create an MSQ question here, right?
Right.
Right. So now this is about what? This is about the topological sequencing, right? Now I will just write down the longest path. Now I'll just update the path. Now I just obtained the longest path to reach each of these vertices, right? So what was longest path to reach this one? Was 1. What about for reaching B? I got 2, right? Sorry,
One,
this is
one,
0.
one.
I'm sorry. This
0
is
and 1.
So
0,
B is 0, 1, sir.
1, 1.
Hmm.
To reach C, the longest path I can have is 2.
2.
And what about this?
2, sir.
3.
3. Ah, yeah.
3, sir.
Now I will just write down against this. Okay. Now look at this. What is the longest path to reach E? 3.
A,
Sir,
D,
1, 2,
A,
B.
D, B, A,
Wait. Just
C,
go in the
E.
order. Just go in the order. What is the longest path to reach E? Is 3, right?
Yes, sir.
So I'm
Yes.
just writing
Yes,
against
sir.
this. You can see
A,
here.
B,
See
E.
my cursor. Wait. Look at my cursor. I'm trying to conclude something here. What about C?
Yes.
2, sir.
2.
2.
What about D?
2.
1.
1.
1.
1. What about B?
1.
1.
What about
0.
0.
0?
0.
This is 0.
Yeah.
Now look at this one thing here.
A.
Now see something commonalities here. Now look at this. This is the longest path to reach all of these, right?
Yes, sir.
This understanding, please make here. It tells you what, if I have to trace back from C to 0, how am I doing it is, I can write E here. Now look at this. In this topological sequence, E was common.
Yeah, for
E
everything.
was common or not?
Yes.
Just tell me.
Yes,
It was
sir.
common.
Common.
A was common.
Yes, sir.
Yes, sir.
Why?
Yes, sir,
Because I had just 1
Yes,
3
sir.
and I have 1 0. Understand this. Noting it down.
Right, sir.
Right? And I had 2 also being same, right?
Correct, sir.
Wait, so I think this C has to be fixed here. Just look at this sequence if this is right or wrong. From A I went to D, then I went to C. I can go to B, right?
From C, how we go to B, sir?
Could you tell me the topological sequence for this? Are we going right?
Topological sequence. Okay.
Topological
Yes, sir.
sequence.
A, D,
First
C.
A. So if I remove A, so I'll be left with what? In
B,
degree
sir.
0 and 0. So I can either choose D. So if I
D,
choose,
C.
so if I choose this D, so I'll be getting this D. Okay.
B.
And then I can choose any, right? So now if I
Anything.
remove this D, then this will have 0. So I can choose B or C.
C.
Right?
Yes.
Yes.
So what do I get? B or
That's
C,
correct.
right? So yeah, so this is fine, right?
That's fine.
That's fine. So now the thing which I was trying to conclude over here was, now I think something error is happening here. It's not fitting over here what I wanted to conclude, but it's all right. You can just leave this part. Maybe I'll just look into this part again and then tell you. Okay. So this part you can forget it right now. I'll tell you in the next session of mine, which is again solve with us. I'll take up this part there and I'll just give you one understanding where this where these two are linked actually. That is something I was trying to create here. I think I missed out somewhere and I'm missing out some calculations over here. So I don't want to give you wrong information. So what I'll do is I'll take up in the next session only that part. Okay. I'll just take the same slide. I'm not changing the slide also. And I'll remind you there that, yeah, this is something I wanted to discuss with you. And over here, I'm just trying to link something, the longest path in DAG to topological sequence. Okay. So how can we link that two things? Fine.
Yeah.
So that, we'll have some inside study. So I'll tell you at that time.
Sir, I got a doubt, sir, on the longest path.
Please tell me.
What I couldn't understand is, this process I understood, but I don't know how it came. What I'm trying to get is that how are these longest paths, because there is no, in these arrows, no weighted average is given. Now we're just assuming, of course we've initialized with 0 and then we are taking the maximum of LPT, let's say V and U, if you have two elements. So without weighted average, how can we say that this is the longest path or the shortest path? And how do we find shortest path here then? Is it some other algorithm or is it?
So shortest path, you will use other algorithm. For DAG, the other application is to find the longest path. So
But without weighted average, how we, all of them have been initialized with 0, right? So maybe A and B is like, let's say 600 and B2 is in terms of, let's say in case of miles, if I say, so A to B is 600 and B2 is only 1 mile. So
okay, that is different concept. What you're asking me is, right, so that is something you will learn in week 11. So don't worry about it. When it is weighted, right, then how do we look at this aspect? So you yourself will be able to comprehend it better. So you wait for this. There are some other theorems, and week 11 is all about theorem. So I think when you see that, then you will be able to understand it. So you just wait for that.
So this one will not be valid or what then?
It will be valid, but it will be valid in different sense when you learn that concept. So you can just keep your patience and keep your enthusiasm. So you will definitely learn that.
So if I'm correct, then instead of 1, we will have the weight in, right?
Again, like if you are giving some weights, then the concept changes there.
No, I think what will change is like in the algorithm, like max this, instead of 1 plus LPT A, it will become the weight to that edge plus LPT A.
Right. Then two aspects. Then again, the theorem changes at that point of time. I cannot use the same. It's kind of not theorem, but it's algorithm itself, right? Because I'm doing the step by step. So the algorithm changes accordingly. I cannot use the same algorithm thereafter because I have to consider that weight aspects as well. So then accordingly, the thing changes. So don't worry about it. You will learn this.
Okay.
Okay. Yeah. So this is about today's session.
Sir,
Yes. One of you had doubt in this activity, I guess.
Sir, one doubt there.
Yes, sir.
So
yes, sir.
Every
Okay,
every sequence, every sequence when you are deriving the LPT, then you are also kind of coming with the topological sequence. What I mean to say is, so when we are deciding the LPT of B, that time the graph is intact, or we have taken out, we have removed A.
You are actually taking it out. You're completely taking it out.
So when we are deciding the LPT of B, then we don't have A. When we are deriving the LPT of D, then we don't have A and B both.
For E, is it?
For D. For
D. At that time, you will consider that A was there, but once you assign a weight for D, then you will avoid A.
Okay. So when we do it for LPT of D, that means A is back, but D is removed.
And when you are already done for D, then yes, there is no arrow for D pointing from E.
No, when we are doing for LPT of D, why we are assigning back A? I mean, why A is back?
You are not assigning any values for A. It's just that it indicates that you are coming from A. And once you assign the value for D, then A's role is gone and you remove A.
So when you
upgrade this weight, this weight for D, then there is no role for E. It's gone.
Okay, so when we are doing LPT of D, that time we have A, D, D you will not have, right? A, D, C, E, B will not be there.
Okay, so when you are assigning for D, but B you haven't assigned. So at that point of time, let's say you haven't assigned for B.
Okay, just one request. To make it simple, can we draw the graph in the that column?
Sure. That's what I was trying to say here. Let's say I am finding out LPT for B. Okay. So what do I do is I first assign, like I remove A, I remove this edge. Okay. Now there is no direct edge connecting. What was the weight for this? Initially 0. Now when I find LPT of B, right? So what do? I first find like the maximum of LPT of B, then 1 plus LPT of
LPT of B, right?
A.
Okay.
Right. So LPT of A will come there. So LPT of A is assigned. Now this is gone, but this is still there. You see, right?
Okay.
Now you go for D. LPT of D is what? I can remove this. LPT of D is what? Or you can essentially do what? You can actually remove both of this. It's just that, you have to keep track a step behind, thinking that the track means what is the initial value of A. I mean, what is the initial longest path of A? That is something you have to keep, because you see this is coming out in your algorithm, right? Because LPT of A is there. Either you remove it or you keep it. It's up to you. But all you have to keep in your mind is when you're coming from A, all you have to do is you have to know what is its weight, right? So you remove it or you keep it, but essentially after you assign the weights for this, you have to remove them, right? That's all.
Okay, sir.
Okay. Yes. So I'll quickly take up that doubt and we can end our session because you're already running short of time now. So yes. So what was your doubt there in?
Actually, I have
No,
yes.
somebody asked me some activity.
Yes, sir. Yes, sir.
Tell
Yes,
me,
sir.
tell me.
Sir, activity 10.4. It is
Just a minute.
regarding BFS.
Fine. I'll just take up that, and we can end after this. 10.4, right?
Yes, sir. The first question.
First question.
Among these four, one.
Okay.
Yeah.
So what are you doing
Like
here? Suppose
among these four graphs, how to find? I could not get it.
Okay, what you have to do is, suppose we perform a BFA so that we visit the vertex and we explore the unvisited neighbors in a random order. Which of the following graph could represent the edges explored by the BFS tree? Okay, so now this is our tree. So I'll just draw that for you, okay? So that you can understand this.
Yes, yes.
Okay. So this is particular question. And what are we doing? We are getting the BFS tree, right?
Yes, sir. Yes, sir.
Right. So we are getting the BFS tree. So let's. Okay, just a minute. You can see my screen, no?
Yes, sir. I can see.
Okay, fine. So maybe I can just take up here. We are drawing the BFS tree. All right. So now look at this. How do you do the BFS tree? Now you'll have to assist me. Fine.
Yeah. Yes.
Okay.
Sir.
So you start with
E, sir. यहाँ पे sir बोल दिया E से start करना.
A से start करने के लिए. So we start with
E
A.
से sir. Not sir. A sir. I think E.
E से बोला है. Okay.
Let
me check that. Let me check that.
Check कर लीजिए. E. हाँ. E sir. E.
E से. Okay. ठीक है. Fine. So let's start with E. So when you start with E, then what do you do?
Then we can from E we can go up to B and C.
You get to B, and then
C.
C. उसके बाद?
Then sir और तो नहीं जा सकते तो सर B से start करना पड़ेगा. कोई एक से start करना पड़ेगा.
तो B से start करो. From B, from B,
B F, A and F and C.
You can go to A.
F.
But C तो already हो चुका है तो you.
हाँ हो चुका है.
Okay.
Yes, yes.
Then from C where all you can go?
And then C से हम जा सकते हैं D और G.
Okay. So now to all of you, is this graph right? Is this BFS tree?
Yes, sir.
Is this a BFS tree?
Yes, sir.
Is there anyone who is saying it's not? All right. So fine. So now let's look at this graph. So now what do you see from here is, now it's basically whatever we have got, it's just shown it in a distorted way. Okay, so now this is your BFS tree. Now,
yes,
okay, now let's look at the graph. You actually have to carefully see this graphs, whatever is given to you. Okay, so now you see that you are starting from E, you can actually go to B, C, right? And from B, you can go to A, F, and from C, you can go to F, D, right? These are the only things which we have. Now look from here. You can actually go from E to where? B, C, and from B, where all you can go to AF, AF, and from C, you can go to GD. So can I say this is correct?
Yes.
Okay. Now, what about the others? I think that is only right, no? That's all right.
हाँ, एक ही है.
और तो उसमें कुछ नहीं बन रहा है, बस वही है.
नहीं.
एक ही बनेगा.
सर मतलब जो जिसमें से रॉन्ग है उसमें कनेक्शन गलत है, मतलब एजेस गलत है जिसमें नहीं हो रहा है.
गलत है. ये तो हो ही नहीं सकता. ये देखो, ये अलग अलग ही हो जा रहे हैं.
हाँ, ये तो दोनों अलग अलग है. डिस्कनेक्ट.
हाँ. तो दूसरे जो है वो तुम देखो.
समझ गया. सो मतलब मैं पहले समझ रहा था कि एजेस सेम होगा, लेकिन और कोई कॉन्सेप्ट है जिसमें बोला जा रहा है कि इसमें डीएफएस है और दूसरे में डीएफएस नहीं होगा.
कोई बात नहीं.
ओके सर, समझ गया.
सर 10.7 का भी एक ऑप्शन मुझे नहीं समझ में आ रहा है, क्या आप देख सकते हो?
इसमें कौन सा ऑप्शन? 10.7 का which one?
Sir, screen is not visible.
Okay. Yes.
Now it's visible,
yes,
right?
Sir.
ठीक है. 10.7 का which one?
Sir, first वाला C और F फॉरवर्ड एज क्यों नहीं है वो मुझे नहीं समझ में आया।
अच्छा, इसके पहले हम लोग DFS ट्री ही बना लेते हैं ना, फिर समझ में आ जाएगा ये। ठीक है, सो दिस इज द लास्ट क्वेश्चन। ठीक है, उसके बाद विल एंड इट। हाँ, ठीक है, I'll just copy it here. So we have to consider the given directed graph. Suppose DFS of the graph is performed from node A. From node A, you are performing a DFS such that when you visit a vertex, we explore its unvisited neighbor in an alphabetical order. Which of the following options is correct, right? So now from A, what we are going to do is we are actually going to do the DFS tree. So when you go from A, so what you do, this is depth first search. So when you go to B, then you will have to go deeper and deeper, right? From A, where can you, so let's start with how professor does, right? So he starts with counter 0, है ना? So right. So when you go to counter 0 say start ho gaya, and then you go to B. So then counter 1 comes, right? From yes. B, where all you can go? Alphabetical order. C. So now counter is what? 2. From C, where all you can go? F. Counter is 3. From F, where all you can go? D. अभी कौन सा है काउंटर? 4. सारे आ गए क्या वर्टिसेस? 5 आ गए फिर तो। हाँ, so now you will go back from D. Can you go anywhere? तो यहाँ पे काउंटर 5 हो जाएगा। ये तो बस we have covered all the vertices, फिर तो counter will reduce like this. ठीक है, so but how many vertices we have? 1 2 3 4 5 6. But how many vertices do we have here? Sorry, how many edges do we have here? 1 2 3 4. How many? 4. But how many do we have here? 6. That means 2 और तो है कोई से, है ना? तो देखते हैं कौन से हैं। From A we can go to B, okay, that's fine. But from A I can also go to where? C. So let me use some different color. Maybe I'll use this. So what is this? A forward edge. ऐसे जा रहा है, A to C जा रहा हूँ मैं, है ना? Okay. Now I have covered how many? Now I am left with one more. Now A का तो हो गया, सारे edges भी covered. From B, are we going where all? I can go to C and I can go to D. I can go to C and I can go to D. So D से भी मैं ऐसे जा रहा हूँ, right? Now there is no other places, right?
Yes, sir.
There is no other. अब तो सारे 6 हो गए, तो मुझे अब देखने की भी जरूरत नहीं है। Now let's look at the option. Suppose DFS of this graph is performed from node A such that when we visit a vertex, we explore its. अच्छा, ये तो ठीक है। Which of the following option is correct? CF is a forward edge. CF is a forward edge?
Yes, sir.
Correct.
No, sir.
नहीं, ये forward edge नहीं है, ये onward edge है। Forward edge इसको बोलेंगे, ठीक है? अच्छा, तो इसमें
what is C2F?
इसको मतलब I'll just give it a name. Onward मैं बोल दे रहा हूँ ऐसे ही। मतलब we have some other name, but I use this. So, but you don't call forward edge, okay?
तो बिकॉज लास्ट सेशन में बोला था कि एक ब्रांच में अगर उस ब्रांच के अलोंग कोई एज कनेक्ट हो रहा है तो उसको फॉरवर्ड बोलेंगे।
हाँ,
इसीलिए मुझे लगा कि C and F फॉरवर्ड हो सकता है।
नहीं, ये तो अभी समझ जाओ पहले, फिर देखेंगे एक बार कंफर्म।
why not forward, sir? I'm not able to get it.
Forward edge is A to C and
It's
B to D.
downwards, no? It's downwards.
No, there is nothing called downward edge.
But it is
if I would have drawn it horizontally, then what you would have called? Cross edge.
No, if it is D to C or F to B, then only it is backward edge, you know?
If it was like this, then you would have called it as backward edge.
But here is C to F, not F to C.
Sorry, it is C to F, right? No, C to F. We are not coming C to F.
So
C to F.
B से है. B to D it is.
Which one? B and D, you're saying?
B to D.
B to D, but B to D it is downward हो रहा है ना? So how could it possible that it's backward? It's not D to B.
नहीं, इसमें एक भी backward edge ही नहीं है, एक भी backward edge है.
That's why I'm asking. There's no backward edge.
अच्छा. And how many forward edges do we have?
Backward edge. That's why I'm confused.
अच्छा. How many? Okay, no problem. How many forward edges do we have? A to C and B to D. कुछ onward edges के नाम बताओ. A to B.
What is
B2C
onward?
onward edges are these normal edges, like
Okay,
simple.
okay, okay.
मतलब I had to give some terms, so I have given this term. It's
सर
like
फॉरवर्ड एज
Just
का सर
like
कॉन्सेप्ट
C to
पूरा
F,
समझा
right?
दीजिए ना.
हाँ
फॉरवर्ड एज समझ नहीं आ रहा है.
फॉरवर्ड एज समझ में नहीं आया, हमें बताता हूँ रुको।
नहीं यार
Forward and backward both, sir.
Forward is can define like
Forward
this,
and backward
the,
both, sir.
like the edge
So
which
backward
goes
is
along the
understandable.
branch but skips some vertices.
Sorry.
It
First,
goes along the
let us
direction of the
complete
branch,
this.
but it skips some vertices. This is our forward edge.
That's what it will be on the same branch, right?
Yes, but
But
skip
it will
some
skip some
vertices.
vertices. Yes,
Yes.
exactly. That's right. So yes, you see this. Now onward edges are many. Like onward edges are like these three edges. So I should not say onward edges, but I should say these are three edges. Okay, three edge, or you can say or onward edges.
Adjacent.
No, adjacent to nahi hota hai, but you can call it. This
something.
is better. Like call it as
Continue
three
this,
edges.
yes.
Maybe even the
Okay.
professor has used this word. So tree edges, right? So AB is tree edge, right? BC is tree edge, right? CF is tree edge, and FD is tree edges, right? So tree edges are right to say. Let's not say this onward edges also. Let's not confuse ourselves. So this is tree edge. What about forward edge? Forward edges, you got this. Like it will be on the same branch, skipping some edge, skipping some vertices. That's somebody told that. Now what about backward edges? Backward edges will be like some arrows going backward. अगर ये back हो गया, it will create a cycle. See, as right, it will create a cycle.
Right.
So only backward edges create a cycle. But for this particular question, we didn't had any backward edges. But right? You notice one. So is CF is a forward edge? Nahi. FD is a backward. There is no backward edge.
Sir, एक बार
AC
फिर
is
से
forward
sir.
edge.
Sir, once more time, sir. CF forward edge about
CF. Now look at CF. CF कहाँ है? CF. ये तो tree edge है. ये तो forward edge नहीं है. Right?
Yes.
CF is a tree edge, but it's not a forward edge. Forward edge में क्या होता है? You will skip one or many vertices basically, right? On the same tree, on the same branch basically.
मतलब सर साइड से
can
चला
you
जाता है.
can you give us example, sir, by diagram? I mean,
अच्छा ठीक है.
For forward edge.
Forward edge का ये जो red में जो बनाया हूँ वो forward edge ही है. This red color one is the forward edge.
मतलब सर साइड से चला जाता है. वो मेन लाइन फॉलो नहीं करता है.
Three edges नहीं होता है.
ओके, समझ गया.
Sir, then A to B, sir. A to B is also forward edge.
A to B is not a forward edge, it's a tree edge.
So B to F?
B to F is a forward edge if we had any, but यहाँ पे कुछ है नहीं, है ना?
Right.
Sir, A to C is a forward edge, right? So
A to C is a forward edge.
A to C is a forward edge. Then A to Y, A to B is not a forward edge.
Because that is a tree edge. Tree मतलब as somebody told, no, forward edge होता क्या है कि forward edge में ना you skip one or two vertices on the same branch, not on the different branches.
Oh, okay, got it.
Okay.
Okay, sir. I got it.
Now look at this. AC is a forward edge.
Yes.
Doubt है कि confirm हो गया? हो
Yes,
गया?
sir. It is a forward edge.
Clear, sir.
FD is backward edge. Backward edge तो है ही नहीं इसमें.
नहीं है.
No backward edge.
CF is a forward edge.
No, sir.
No,
नहीं,
sir.
ये तो tree edge है. ये तो नहीं हो सकता.
BD
is a backward.
is backward edge. No, sir.
Backward edge तो खैर है ही नहीं तो होता. फिर एक ही करेगा.
सर एक्सक्यूज मी, बैकवर्ड एज में भी एक वर्टेक्स स्किप होता है क्या?
बैकवर्ड एज में हाँ कितना भी हो सकता है, ऐसा ही होगा.
एक वर्टेक्स स्किप होगा, राइट?
No, not necessary. You can
Not necessarily, ऐसे भी हो सकता है.
अच्छा,
ऐसे भी हो सकता है.
सर बैकवर्ड एज मतलब सर फॉरवर्ड के उल्टा डायरेक्शन पे होगा ना?
उल्टा डायरेक्शन में होगा, करेक्ट.
ओके.
ठीक है.
ऐसे भी हो सकता है, मतलब एक ही एज में हो सकता है, बीच में स्किप नहीं हुआ तो भी.
हाँ, ऐसे भी हो सकता है. जैसे कि अगर तुम
B2F.
सोचो, अगर मान लो ऐसा था कुछ, ऐसे था कुछ, ठीक है, ऐसे था कुछ सपोज, है ना, तो यू कुड कम फ्रॉम A to B, बट ये भी तो हो जा रहा है कि आप ऐसे भी जा रहे हो B to A.
तो फिर तो C to F में भी अगर ऐसा किया तो साइड से तो.
अच्छा चलो ठीक है, इसका हम लोग बनाते हैं. ठीक है, यहाँ पे ये हो गया. थोड़ा और इसको और वो कर देते, रुक जाओ, तुम लोग एक और में देता हूँ. तो थोड़ा मुझे पता नहीं था कि नहीं आता है. ठीक है, तो लेट मी टेक दिस, ये बहुत पहले मैंने यूज किया था ये स्लाइड को, इसी को ही मैं रीयूज करता हूँ, ठीक है। सो ये तो डैग वैग को हटा दो, ऐसे हम लोग बस इसका ये बनाते हैं कि फॉरवर्ड एज बैकवर्ड एज समझ लीजिए, ठीक है। यहाँ पे डैग वैग का कुछ नहीं है, ठीक है, सो डू नॉट गेट कंफ्यूज, ये कुछ नहीं है, ये सब चीज को भूल जाओ, सिर्फ ये ग्राफ को हम लोग यूज करेंगे, ठीक है। दिस इज नथिंग, ओके। सो आई एम जस्ट ट्राइंग टू ड्रॉ, तो ज्यादा बड़ा हो जाएगा, ये टाइम लेगा, सो आई विल नॉट यूज दैट, सो मे बी आई कैन यूज समथिंग एल्स, या फिर इसी एग्जाम्पल पे ही ले लेता हूं मैं, ठीक है, कि लेट्स से यू हैड समथिंग लाइक दिस, ये इससे कनेक्टेड था ऐसे, just give me a minute, am I audible?
Yes, yes, you are audible.
Okay, actually power went off here, I'll just connect my cellular.
Oh.
Just check outside. Oh, it's this hour. Yeah. Now I think it should be fine.
একটা help করে দেবে?
A minute. Okay. So now I was just telling about this backward edges, right? Am I audible? I'll mute you all.
হ্যাঁ, একটা help করে দেবে?
Hello?
Yes.
Am I audible?
Yes.
Yes. So now let's say if I was trying to draw the DAG for this, okay? So and I have to follow the same alphabetical order. And let's say there was one more edge like this. Okay? It was somewhere like this. So what I'll do, I'll go A to B, B to C, C to F, फिर D and all that, right? And इसमें देखो अभी क्या हो जा रहा है, एक backward edge आ जाएगा, right? It'll come, right?
Yes, sir.
Yes.
This is something will come like this.
Yes, yes.
तो इसमें backward edge है, एक है, right? So need not be कि it has to jump and go over here. हाँ, but forward edge होने के लिए उसको एक तो जरूर jump करना पड़ेगा.
हाँ हाँ, right.
Right?
क्योंकि already सर है ही, तो मतलब edge तो है ही.
हाँ.
Already एक तो है ही.
ठीक है, so understood this.
Yes, sir.
Yes,
yes, sir.
ठीक है, so we can end our session then.
Thank you, sir.
Yeah, thank you, sir.
Thank you,
Thank you, sir.
सर
Yeah.
Thank you, sir.
Yeah.
Thank you, sir.
You're welcome.
क्या आप पहले वाले स्किल बता सकते हैं एक क्वेश्चन?
कौन सा वाला?
अभी रिसेंट जो आपने,
कौन सा वाला बताओ?
अभी जो आपने बताया ना,
ये वाली कर्सर दिख रहा है मेरा, ये वाली?
Your screen is not visible.
Yes, screen नहीं आ रहा है.
sorry. Okay.
सर
फिर से बताना है उसे?
नहीं सर, एक बार बताऊंगा
इसको?
हाँ सर.
अच्छा, ये मैंने अनएडिटेड वाला कि पहले वाला?
हाँ नहीं, ये सर हमने ए के बाद में बी लिया, अगर हम ए के बाद में सीधा सी ले लेते तो फिर AC is not forward edge.
नहीं, बट फिर वो हमें क्या करेंगे, उस समय हमें अल्फाबेटिकल ऑर्डर में जाना है.
हाँ सर.
इसीलिए ये डाउट मुझे भी हो रहा था पहले, लेकिन फिर बाद में जब देखा ध्यान से कि हाँ अल्फाबेटिकल ऑर्डर, तो फिर ये पूरा प्रॉब्लम सॉल्व हो जाएगा. ठीक है?
यस, थैंक यू
सर. एक्चुअली मैं सर जहाँ तक मुझे समझ में आया, फॉरवर्ड एंड बैकवर्ड एज, फॉरवर्ड एज इज दैट पार्ट ऑफ लाइक व्हिच इज नॉट पार्ट ऑफ DFS tree and directly I mean it is descendant of that link, sir. But backward is not part of DFS tree and it is not an ancestor of that part, sir, isn't it, right, sir?
नहीं, वो ancestor भी है.
Backward is ancestor है.
हाँ, ancestor भी है.
मतलब वो ancestor वो नोड का ancestor है ना सर?
हाँ, मतलब ये ओरिजिनल ग्राफ का पार्ट है वो. इस केस में मैंने ऐसे एक बनाया था, मैं बोला कि हाँ एक ग्राफ अगर सपोज ऐसा है तो फिर कैसे होगा. दैट वाज द थिंग. मतलब जैसे कि अगर यहाँ पे जैसे कि अगर मैं एक बार फिर से बता दूं, तो होता क्या है कि इफ यू हैव अ फॉरवर्ड एज, तो फॉरवर्ड एज में क्या होना है कि उसको उसी ब्रांच में रहना जरूरी है, पहला कंडीशन. और एक वर्टेक्स तो कम से कम उसको स्किप करके जाना है. जैसे कि यहाँ पे आप देख सकते हो कि डी को तो स्किप कर ही रहा है, एक वर्टिसेस को तो स्किप करके जा ही रहा है, राइट। ऐसा ही आप इसको देखोगे तो देखो 2 वर्टिसेस को स्किप कर जा रहा है, मतलब एक से ज्यादा वर्टिसेस को जरूर स्किप करके जाएगा वो, इसीलिए हम इसको फॉरवर्ड बोलते हैं कि जहाँ ये फॉरवर्ड एज है। अदरवाइज हम उसको डायरेक्टली बोल सकते थे, ऐसे तो इसको भी बोलते हैं, ए बी को भी बोल सकते थे।
अच्छा, मतलब ये एक स्किप करके जा रहा है, मतलब
कम से कम एक
ए टू सी, मतलब वो इनडायरेक्टली आ रहा है ए बी सी होते हुए, राइट?
हाँ हाँ हाँ,
ए बी सी होते हुए, मतलब ए सी डायरेक्ट नहीं ना?
हाँ,
ओके।
ए सी डायरेक्ट क्यों नहीं ले रहे, हम लोग ले सकते थे, बट यहाँ पे बोला गया कि नहीं, तुम्हें अल्फाबेटिकली ही परफॉर्म करना, तो अल्फाबेटिकली ही परफॉर्म करना है, तो ए के बाद तो मैं बी ही जाऊंगा, राइट?
करेक्ट।
हाँ, लेकिन ये ग्राफ क्या बोल रहा है कि नहीं भाई, तुम सी के पास भी जा सकते हो, तो वो अगर होगा, उसको अगर अकोमोडेट करना है तो उसको हम फॉरवर्ड एज की तरह अकोमोडेट करेंगे।
उसी तरह फिर बी टू, ये जो बी सी और एफ होते हुए डी जा रहा है, राइट?
हाँ, उसी तरह ऐसे ही जा रहा है, करेक्ट। तो देखना आपकी वो सेम उसी ट्री में ही है, उसी ब्रांच में है, पहली कंडीशन उसी ब्रांच में होना चाहिए, और कम से कम एक वर्टिसेस को स्किप करके जाना है, ऐसा होगा, ठीक है। लेकिन बैकवर्ड एज में क्या हो रहा है, वो सेम ब्रांच में ही रहेगा,
रिवर्स में जा सकता है,
रिवर्स में जाएगा, बट नीड नॉट बी कि जहां उसको एक जंप करके मतलब जरूरी नहीं है कि उसको जंप करने की जरूरत है, वो मतलब वो उसी से ही कनेक्टेड हो सकता है, जैसे कि मैंने अभी एग्जांपल बताया है ना। हो सकता है ऐसा भी हो, डी से ए के पास जा रहा हो, चाहे डी से बी के पास जा रहा हो सकता है।
हो सकता है, मतलब एक भी जंप करके जा सकता है, और सीरियल वाइज भी जा सकते हैं,
सीरियल वाइज भी जा सकते हैं, कितना भी जा सकते हैं, ठीक है।
क्लियर हो गया सर अभी,
ठीक है। और होता है एक और वर्ड होता है, उसको बोलते हैं क्रॉस एज।
ओके, क्रॉस एज।
हाँ, तो इसको भी आप नोट कर सकते हो कि क्रॉस एज में क्या होता है कि अगर हमारे पास एक और ऐसा अगर ब्रांचेस रहता, लेट्स से कहाँ तक पहुंचे थे हम लोग, एफ था ना, यहाँ पे जी है और एक और डी है, तो यू सी दिस क्रॉस एजेस क्या होता है ना कि 2 ब्रांचेस से कनेक्टेड रहता है, मतलब हो सकता है ये इससे ऐसे आ गया, समझ में आया? तो इसको हम क्या बोलेंगे कि हाँ ये क्रॉस एज है, ये नाम ही बता रहा है कि हाँ ये मतलब 2।
अच्छा, वो मिक्सिंग ऑफ फॉरवर्ड एंड बैकवर्ड, दैट मींस it is a edge like which connects two nodes such that like they do not have ancestor and descendant relationship, right? Okay.
और आप ये भी देख सकते हो कि ये क्रॉस एज जो है ये साइकिल क्रिएट नहीं कर रहे, है ना? साइकिल क्रिएट कर रहा है? नहीं कर रहा,
नहीं।
तो सिर्फ बैकवर्ड एज ही साइकिल क्रॉस क्रिएट करता है। तो आप इस टर्म्स को नोट कर सकते हो कि ट्री एजेस क्या होता है, फॉरवर्ड एजेस क्या होता है, बैकवर्ड एजेस क्या होता है, क्रॉस एजेस क्या होता है।
अब क्लियर हो गया सर?
क्लियर ना? तो ये सब वर्डिंग्स इंपॉर्टेंट है ये, ठीक है।
थैंक यू सर।
ठीक है, तो फिर
क्वेश्चन में न्यूमेरिकल ऑर्डर और अल्फाबेटिक ऑर्डर ही प्रेफर करना चाहिए।
हाँ, मतलब वो हम लोग बोल भी देते हैं कि हाँ यू हैव टू फॉलो दिस ऑर्डर। मोस्ट लाइकली हम लोग हर क्वेश्चन में बोल देंगे कि आपको यू हैव टू फॉलो दिस ऑर्डर, ठीक है।
Okay, thank you sir, it was a nice session sir.
Yeah,
thank you sir.
Thank you sir, good night. Good night sir.
End our session. Yeah, thank you, good night.
Thank you sir, good night sir.
Good night.